All right, so welcome to this very special training for the CompTIA SecAI Plus exam. My name is Alex. I'm going to be your instructor. Now, before we begin, I want to give you some very important information about this mega tutorial. First of all, according to the official exam objectives for SecAI Plus, we have 4 main domains. So this tutorial will cover in full domains 1 and domain 3. So all in all, you're going to get about 41% of the entire exam objectives from this tutorial. I should also let you know that all the lessons you're going to watch in this tutorial have been modeled. They've been tailored specifically after the official CompTIA SecAI Plus Set Master Study Guide. So you can see right here, this is the official training from CompTIA themselves. So everything you're going to watch in this video, all the lessons have been designed specifically from the official CompTIA training itself. Now, I'm also going to provide for you a free download, okay? This is going to be a PDF summary guide of the entire domain 1. So you can think of this as a resource, as a book that you can read and use at your own free time. I'll have a link for you down in the box below. I'll have more information about the actual main course itself. But for now, let's begin the training. All right, so welcome officially to the very first section of our course. And I know, yes, on the slide you see section 2 for the course curriculum, but actually in the CompTIA Learning platform, this is actually section 1. All right, so it is the very first official section, AI Fundamentals for Cybersecurity. And of course, because the certification is all about AI and cybersecurity, we have to start from the basics. So before you can defend against AI-powered cyber threats or even use an AI security tool, you need to understand what exactly AI is from the ground up. So we're going to have about 9 lessons. We're going to explore the 5 core AI types. And then, of course, you'll also have some real-world skills by the end of this course. So what exactly are you going to learn? The core AI concepts, what generative AI is, what deep learning is, what machine learning is, transformers, and so on. And then, of course, is the machine learning-powered threat detection, as well as the benefits and risks of AI in security. So why does this matter? Well, AI is obviously reshaping the threat landscape. We now know that hackers can use AI to create all kinds of new cyber attacks. So the SecAI Plus framework starts here with the fundamentals that makes everything else possible. So without wasting any more time, let's jump right in. All right, so welcome to the very first official lesson. And here we're going to be talking about the core AI types in cybersecurity, basically the foundational concepts. And we do have to start from the very basics, which is, of course, what is artificial intelligence? And it all depends on who you really ask. There have been different kinds of explanations or definitions of what AI is, but in general, it's simply machines being capable of problem solving and analysis with minimal human direction. So we have machines that can process data, make decisions with little to no human oversight. That's basically what AI is. And there are 3 fundamental concepts that we're going to be concerned with as far as AI is concerned with cybersecurity. First is that AI tends to learn from data. There is a reason why I very often tend to say that data could be like the lifeblood of any AI model. How sophisticated or how capable an AI model is depends very heavily on the quality of the data with which it was trained with. So again, AI tends to learn patterns from data and then can also act autonomously. So basically make decisions on its own. And because we now have AI in cybersecurity, obviously it has transformed the way we do certain kinds of things within the world of cybersecurity. Now, as with any kind of new technology, it's always dual purpose, okay? We always have technology that can be used either for good or for bad. There is almost no kind of technology that cannot be used for one or the other, or both, basically. Now, when it comes to the benefits of AI within cybersecurity, yes, we now use AI for threat detection. We can identify attacks a lot quicker and also prevent them from even occurring a lot quicker. Predictive analytics also anticipate risks before they materialize. This is something that firewalls and anti-malware have been using for a very long time. And then, of course, SOC automation. streamline repetitive security operations. So things like extracting IOCs from security reports, going through log files, all these kinds of things can be done with AI now. With all that being said, all the good, now we also have the new risks involved with AI. Of course, we now have new vulnerabilities because AI systems can be hacked. And of course, we're going to delve very deep into that later on in this course. We do have governance gaps, inadequate oversight of AI decision making. In fact, there's big issues involving the ethics of AI. And then flawed algorithms. We have AI machines and models making very biased decisions or misconfigured models that end up causing different kinds of failures. Again, we'll delve deeper into this later on in the course. And then training data risks. So basically sensitive data mishandled during model training. These are all different kinds of risks associated with the introduction of AI. Now, there's going to be 6 key AI concepts that we need to familiarize ourselves with for cybersecurity. The very first is, of course, generative AI, which is what we know today. ChatGPT, Claude, Gemini, basically any kind of AI model that can be used to create text, images, videos. That's generative AI. We do have machine learning, which, again, we'll delve deeper into this, but it's basically kind of like the OG of AI. It all started from machine learning, basically the ability of machines to learn from historical data, to then make predictions and classifications, and then statistical learning, which explains why models make specific kinds of predictions or give certain kinds of results, basically interpretability. Are we able to understand why this particular AI model reached this conclusion? We'll talk more about this later. And then, of course, transformers, breakthrough architecture that powers modern AI sequence tasks, deep learning, which is the multi-layered neural network solving highly complex tasks, and then, of course, NLP, natural language processing, which enables machines to read, interpret, and then generate human language. Again, we're going to delve very, very deep into each one of these 6 concepts and how these AI types relate. Again, it all starts from the very top, which is AI, the broadest field. And then you have statistical learning or machine learning. You have deep learning, which is a subset under machine learning, which then gave rise to transformers, which then is used for NLP and generative AI. So you can see that they're not down there. It says AI is a broad field. Each concept builds on or extends the one above it. Understanding this hierarchy will help us as security professionals pinpoint where vulnerabilities and capabilities merge. Now, why this matters? Because, well, security professionals who understand AI will be able to harness its power and also contain its risks. So yes, as security professionals using AI, we need to harness the full power by deploying AI tools effectively across the security stack, being able to identify the risks associated with the use of AI. And I'm telling you, there's a whole bunch of them. And then, of course, stay proactive, mitigate AI associated risks before they are even exploited. So that's basically it for the introduction to the world of AI. Thank you for watching. I will see you in the next class. Welcome to lesson 2. And here we're going to take a look at the types of AI. I do have my introductory note there that says, from humble pattern matching algorithms to systems that can now write code, compose music, and even generate images. It truly is outstanding just how very quickly AI has evolved. A lot of people tend to think that AI started with ChatGPT and Claude. That's not necessarily true. That is generative AI. AI has actually existed for decades. Your earliest forms of anti-malware, firewalls, they all used AI in some form. So anyway, this lesson here is going to trace the journey right from the very humble beginnings of AI to where we are currently. So how AI types have evolved. Now, AI isn't just one single technology, all right? It's a very, very broad field, a family of related approaches that have built on each other over decades. So understanding this lineage will help you recognize what each AI type is good at, where it came from, and why it does matter in modern security contexts. And right there, you can see the diagram. It all started from machine learning. The ability of machines to make predictions and analysis based on recognizing patterns from data. And then for machine learning, we had a subset called deep learning, which introduced neural networks for much more complicated tasks, and then transformers, which then enabled AI models and machines to understand language, which then gave birth to generative AI. So each layer builds on the one before it. Machine learning laid the statistical foundation. Deep learning added neural complexity. Transformers unlocked language understanding, and generative AI produces entirely new content, all starting from the first insight that computers could learn from data. So please, for the exam, you need to know this. It all started from machine learning, again, laying the very foundation. Deep learning added neural complexity. Transformers unlock the ability to learn and understand languages. And of course, generative AI allows the models to produce content. Okay, so machine learning, let's start from the OG itself, machine learning. So this is the foundational branch of AI. Instead of following the usual handwritten rules, ML models were able to make predictions and learn patterns directly from data, and then use those patterns to make predictions. So it was all about the quality of the data. If you fed AI models with very, very good data, plenty of it, over time, that model will be able to learn certain kinds of patterns, and then we'll be able to start making predictions. So the core concept here is that no explicit programming is needed. We're not saying, hey, AI, whenever you see A plus A, that means it's going to be 2A. Whenever you see A plus B, that means it's going to be AB. No, instead, the model will improve its own performance by processing examples and adjusting internal parameters. Think of it as self-studying, right? Imagine you trying to learn a new kind of language, okay? And instead of you going for lessons every single day, you teach yourself. That's basically what ML kind of is, right? So the classic example is the spam filter. I promise you, all the textbooks and other lessons you take on machine learning, they always use the spam filter because it's kind of like the very best example we can give. So a spam filter analyzes thousands of labeled emails. We'll talk about labeled data a bit later. Learns what spam looks like. So basically, the idea here is that you're trying to train a spam filter. The very first thing you will do is that you're going to give it plenty of examples, and you're going to label those examples. You need to let the machine model know that, okay, what it's looking at, what it's processing is a spam email. And then you imagine you gave that machine model thousands of different types of spam emails. Eventually, with time, this machine model, because it's starting to see certain kinds of patterns within all these spam emails, it will be able to make better decisions and get more accurate over time. The primary goal is to maximize the accuracy of the predictions. Yes, we know that machine learning models, they can make predictions, but how accurate are those predictions? That's the goal. The goal is to maximize the accuracy of those predictions. So the model is evaluated on how well it generalizes to data it has never seen before. All right, statistical learning, kind of like the opposite side of machine learning. It is the theoretical backbone behind most ML algorithms, rooted in mathematics of probability and inference. So how is it different from the traditional machine learning? Machine learning will focus heavily on predictive accuracy. Statistical learning asks a much deeper question, which is, why did this particular model make this particular kind of decision? We're basically trying to understand the rationale behind the AI making a certain kind of decision. So statistical learning is a subfield of statistics that provides the theoretical foundation For many ML algorithms, including linear regression, logistic regression, and support vector machines, it emphasizes interpretability, confidence intervals, and understanding the relationship between inputs and outputs. And in cybersecurity, interpretability matters. Knowing why a model flagged an event is just as important as knowing that it did. Now, I want to tell you something, okay? And this is just for general knowledge. It's not necessarily for the exam itself. But overall, interpretability is extremely important when it comes to AI development. And usually, the more advanced, the more sophisticated an AI model is, the less likely it is going to be for us and even the developers of that AI model to understand why it made certain kinds of decisions. So basically, there's this constant trade-off between interpretability and efficiency. The more interpretable an AI model is, the less efficient it's likely to become. But the more efficient, the more powerful an AI model is, the less likely we will be able to interpret why it made certain kinds of decisions. And this is very, very important. Interpretability is very important, not just in cybersecurity, but in pretty much any kind of field where AI is used. Imagine in the medical field, we now have AI being used to run diagnoses. Now, if the AI reached a certain kind of conclusion and recommends a certain kind of treatment, the doctor in charge of that patient needs to understand why the AI model made that decision. The doctor just can't go with the recommendations of the AI model blindly, because this is high stakes. Any mistake could prove fatal. The patient could die. That's why interpretability is very, very important whenever AI is involved, not just in cybersecurity. So from machine learning now to deep learning, which is a subset of machine learning, and it's inspired by the brain. Anytime you see deep learning being symbolized, it's typically the human brain. Why? Well, because it uses multi-layered artificial neural networks loosely modeled on how our actual biological neurons in the brain connect and fire. So, three main parts. You have a layered architecture. Each layer in a neural network will learn increasingly abstract features. Early layers will detect edges. Later layers will recognize faces or objects. We'll delve into this a bit later. And then, of course, image recognition. It is through deep learning that AI models are able to interpret images. So deep learning powers facial recognition and medical imaging systems, achieving human-level or superhuman accuracy on visual tasks. And of course, speech and NLP, voice assistants, and real-time transcription systems rely on deep learning to process audio and natural language at scale. And then, in 2017, came the breakthrough, transformers, a turning point within AI. Now, why? Well, the transformer architecture unlocked a new way of processing sequences of data, like words that you will have in a sentence, that was dramatically more efficient and powerful than anything before it. I want to say something real quick here. You may already know this. You may have noticed. But if you haven't, here's the thing. If you told ChatGPT or Claude, Gemini, any AI model, if you gave it a sentence, say something like, I want you to print my email files, just as an example. Did you know that if you didn't include certain words like I, you, a, add, like filler words, if you don't include them in the sentence, the AI model will still understand what you are trying to say. That is because of transformers. It allows AI models to very quickly be able to recognize what it is that you're saying, even if sometimes you provide incomplete sentences. It's all because of transformers. So rather than reading text word by word, transformers will use a mechanism called self-attention to understand the relationship between all parts of a sequence simultaneously, unlocking unprecedented language understanding. So again, you don't have to provide a full, complete sentence, a grammatically correct sentence. You can omit prepositions or conjunctions or even pronouns, and the AI model will still understand what you're saying. So key applications: language translation and summarization, writing and completing text, computer vision and image analysis, drug discovery, and protein folding. So before transformers, models had to process sequences step by step, struggling with long-range context and slow training. Imagine the AI model having to go through every single word in a paragraph, right? Or even in an essay. But after transformers, parallel processing of entire sequences, leading directly to GPT, BRT, and modern generative AI. Okay. And because of transformers, we now have what we call as AI today, generative AI beyond recognition. So Gen AI represents the cutting edge of the AI evolution. Earlier AI types were designed to classify or predict. That's basically what it was. You would have your AI models that can either make classifications or simply predict based on patterns it has recognized. But with Gen AI, we can now actually create new kinds of content. Built on deep learning and transformer architectures, it can produce entirely new, original content that didn't exist before. As I'm recording this video, there is this video generator called CDance 2.0 that's from China. As you're watching this video, you probably know the AI model I'm talking about. It has gone crazy, making all kinds of videos. There's the one between Brad Pitt and Tom Cruise fighting. There's this new one on Facebook where I see this cat constantly, doing martial arts with like a kung fu master, and then it's talking. It's so funny. Anyway, with Gen AI, of course, we can create text, images, music, write code, make videos, and so on. So the AI family tree at a glance. You need to know the structure for the exam. Please pay very, very close attention. Again, at the bottom is AI, and then you have machine learning, which can either be statistical learning or deep learning, which is, of course, a subset of machine learning. And then you have transformers, and then you have generative AI. So please study this particular diagram for as long as you can. So every generative AI system you interact with, from chatbots to image generators, is built on this entire stack. Cybersecurity professionals like you must understand each layer to assess risks, identify attack surfaces, and apply the appropriate control. So why AI types matter in cybersecurity? Each AI type will introduce distinct capabilities, but also vulnerabilities and risks. So knowing the type of AI that a system is working with will help you anticipate what it can do and also how it can be exploited. Very, very, very important. All these different types of AI, they provide different kinds of capabilities, but they also have different kinds of vulnerabilities. So ML and statistical learning, you can use this for power intrusion detection and anomaly detection systems, kind of like in your firewalls, your anti-malware, your threat awareness systems, things like that. And then vulnerable to adversarial inputs and data poisoning attacks that corrupt the training data. Now, for deep learning, we can use deep learning for facial recognition, threat detection in images, network traffic, voice. The risks here are model inversion, and then extraction attacks targeting sensitive training data. And then for transformers and generative AI, of course, we can use this for our chatbots, security co-pilots, log analysis, and so on. However, it introduces new kinds of risks like prompt injection, hallucination, and AI-assisted phishing at scale. In the next module, we're going to delve very heavily into AI security. So some key takeaways, again, machine learning. Computers learn patterns from data to make predictions, no explicit programming required. Statistical learning tries to explain why a machine learning model made a certain kind of prediction. So it focuses on interpretability. Deep learning uses layered neural networks inspired by the human brain for much more complex tasks like image and speech recognition. Transformers enable parallel sequence processing, the foundation of modern language models, and then generative AI built on deep learning and transformers that can be used to generate new text and different kinds of content. Thank you for watching. And of course, I will see you in the next class. Let's now take a look at generative AI in cybersecurity. And the purpose here is to understand exactly how generative AI can be used for both offensive and defensive purposes. So what is generative AI? Well, basically machine learning models that have been trained on massive amounts of data sets to produce entirely new content like your videos, images, and so on. And then how it works is that they will analyze statistical patterns across billions, possibly even trillions of data points. And then once trained, they will have the ability to generate their own outputs on demand, making them very versatile. And of course, we've seen generative AI being used across different kinds of industries, from social media to finance to healthcare to security, cybersecurity, and so on. So in cybersecurity specifically, Gen AI can be used for both offensive purposes and of course defensive purposes. Now, offensive use cases of generative AI, one of the most common right now is phishing simulations. You have cyber criminals being able to create very sophisticated and very convincing looking types of phishing emails with the use of AI. And then of course, creating unique malware signatures that will bypass your traditional signature-based detection tools, using AI to create polymorphic code, and of course, AI being used to create deceptive content, such as deep fakes, which can be used to spread disinformation. But defensive use cases, we can also use AI, or generative AI rather, for red team threat scenarios where they can create or generate very realistic, varied attack scenarios for exercises, which will enable more comprehensive security assessments, and also for security awareness training. In fact, only a few weeks ago, one of my clients, they were able to use Claude specifically to create some very convincing looking types of phishing emails to test the awareness of their employees. So we're seeing generative AI being used to create content for security awareness training, and then of course preparing for generative threats. Model AI generate attack patterns to help organizations build detection capabilities and response playbooks specifically designed to counter the adversarial use of generative AI. So what are the risks of your Gen AI systems? Well, first of all, you have one of the most common issues, which is the biased or misleading output. So a lot of times we may have AI systems either because they are simply hallucinating or because they were trained with very poor corrupted data, or maybe even data that was biased. So guess what? Any AI model trained on biased data will end up giving you biased outputs. And then of course, exploitation by adversaries. You have different kinds of attacks like your prompt injection, model poisoning. We're going to take a look at them individually later. And then of course, the extraction of very sensitive information. So any models that are trained on proprietary data may inadvertently leak confidential information through crafted prompts. Now, I do need to point out that the extraction of sensitive information, it's not just the extraction of the proprietary data with which the models are trained with. A lot of times, it could even be the sensitive data that the users themselves uploaded to their favorite AI model. You have a scenario where somebody uploaded their own medical records to ChatGPT, to the public free version of ChatGPT, and somebody ends up getting access to that information. So that's just an example of the sensitive information extraction. All right, practical example, OpenAI API for security testing. So we do have an API specifically for OpenAI. It's called the OpenAI ChatGPT API. And with the use of Python, we can actually use ChatGPT to create realistic business email compromise phishing simulations for controlled security awareness testing. So this would allow the security teams, the security awareness training coordinator, to produce high volume contextually relevant phishing content tailored specifically to different types of departments, job roles, industries, and so on. However, with that in mind, if you want to be safe, because we're using an API key here, we have three main ways to ensure that key isn't exposed. First of all, we're going to use a secrets vault. So we will store all the API keys in tools like your HashiCorp Vault or AWS Secrets Manager, rather than hard coding them in source files. Another way is the use of environment variables, where at the minimum, we will only load the API keys from environment variables at runtime specifically to prevent accidental exposure. And then of course, just like with passwords, we can rotate and audit the API keys. So these are 3 ways how we can ensure API key security best practices. Know them for the exam. So generative AI in a nutshell, it's a double-edged sword. You have the good, you have the bad, you have offensive, you have defensive. So we can use generative AI for threat simulation, red team exercises, awareness training, detection improvement. But we can also use generative AI for phishing generation, malware crafting, polymorphic code, and disinformation at scale. So the same underlying capability that will enable security teams to simulate attacks, train defenders, is also accessible to adversaries and cybercriminals who might be seeking to automate and scale their operations. So governing and securing AI systems, organizations that deploy generative AI must establish robust governance frameworks, not just for compliance, but also to prevent AI systems from becoming liabilities. So different ways to approach this. First of all, we're going to have to define the AI use policies. So we'll have to establish very clear, acceptable use policies that will govern which generative AI tools are approved, how many outputs may be used, and who holds accountability for the AI generated content. So there needs to be policies that will guide the use or restriction of AI within an organization. And then, of course, secure the API pipeline, apply zero trust principles to AI infrastructure. So this would include things like restricting API access restricting API access, monitor the usage patterns, implement input and output filtering, and of course, preventing prompt injection attacks. And of course, we'll also have to monitor for either the misuse or drift within AI. So we'll continuously have to audit every single output made by the AI for any possible signs of manipulation, contamination, model drift, or adversarial abuse. So we're going to integrate AI activity logs into your SIM for correlation and anomaly detection. And of course, we can also train security teams. We'll ensure they understand the capabilities of Gen AI, the different kinds of attack surfaces, the vulnerabilities, the risks associated with the use of the Gen AI, as well as the defensive application. So basically, we're making Gen AI literacy a core competency in the team. And of course, it's no surprise that now, and of course, in the near future, cybersecurity professionals will be expected to know how to work with AI. There is no escaping it. So key takeaways. First of all, Gen AI can create new content. It is a double-edged sword, as we've explored. Governance is non-negotiable. We do need to ensure that the way AI is used in our organization is governed, because it is an extremely powerful tool. And of course, literacy is a core competency. Security professionals who understand generative AI, its capabilities, risks, and attack vectors are far better equipped to defend against AI-powered threats. Thanks so much for watching, and of course, I will see you in the next class. Welcome back. Real quick, hope you're enjoying the training thus far. I just wanted to take a minute to talk to you about my main course itself on my platform lab, cyber.com. This is the course right here, and unlike this free tutorial that covers only domains 1 and 3, the main course itself will cover all the 4 domains, obviously. Now, in addition to covering all the 4 domains, you will also be tested with over 200 quiz questions. There will also be an exam at the end of the course. That's basically a simulation of the main exam itself. And in addition to covering all the 4 domains, I'm also going to provide for you access to all the slides used in the creation and presentation of this course. Here's an example. Here is the slides for lesson 2.1.3. So I'm going to give you access to all the slides, over 100 of them. And of course, I'm going to give you access to all the PDF guidebooks for each and every one of the modules. I've given you access to module 1. Here is module 2. So you'll get access to modules 2, 3, and 4 as well. And of course, you will also have access to me. If you have any questions or you need any help, I will be there to guide you and help you out. So I'm also going to offer you a very special discount. Normally the cost is $107 US, but I will be offering a very special 25% discount. Now, how you can get your hands on this discount is basically to opt in using the link down in the box below. When you opt in to get the Module 1 summary guidebook, in that email, you will also have access to the very special coupon that will give you a 25% discount. So if you're interested in actually taking the main course on my platform, labcyber.com, I'll have all the information for you in the email using the link down in the box below if you choose to opt in. And as always, if you have any questions or concerns about this course, you're more than welcome to ask me. You can post your comments down in the comment section below. I will answer and respond to all questions and queries. So without wasting any more time, let's continue with the rest of the training. Let's now move on to a very important part, which is of course machine learning and statistical learning. So machine learning, we've talked about it already a few times in the course already. Basically, it's the branch of AI that would allow machines or computers to learn from data, identify patterns, and then make decisions. So there is a level of autonomy associated with machines trained on machine learning. And we typically will use them for things like your spam detection, recommendation engines, image recognition, and so on. Now, in cybersecurity specifically, of course, we've been using ML with firewalls, anti-malware for the longest time. But today we can use ML for predictive threat modeling, for task automation. So very repetitive kinds of tasks. Again, log parsing, alert triage, we can use ML for that. Your SIM and EDR augmentation, we can integrate machine learning pipelines with your favorite SIM tools like your Splunk, Elastic, QRadar to enhance our detection capabilities. And of course, reduced analyst fatigue. We don't need analysts going through thousands of logs anymore. ML can do that for them. All right, now there is this core concept you need to be aware of when it comes to machine learning. There are two types. So you have the supervised learning and then the unsupervised learning. With supervised learning, the kinds of data we're going to train the models with, they are labeled, okay? Say, for example, as usual, the classic spam filter machine, right? When you're training a spam filter, it needs to know what exactly what exactly a spam email would look like. So we're going to label the data and say, okay, this is spam, this is spam, this is spam, this is legitimate, this is legitimate, this is spam, this is spam, this is spam. And then over time, that ML will be able to begin to recognize what a spam email actually looks like. So it's trained on labeled data sets. Each example has a known outcome. For example, malicious or benign. It's best for known threat patterns. Again, spam, malware classification, phishing detection, high precision, and auditability. These kinds of machines are very, very precise in their decisions and results. It does require quality labeled data though, which can be expensive to produce. And then of course, example algorithms will be your decision trees, SVM, and random forest. But what about the unsupervised learning? Basically, we are leaving the machine to learn on its own. So it'll discover structure in unlabeled data, no predefined categories required. So it is best for unknown or zero-day threats. Again, with supervised learning, it is best when we know exactly what the threat looks like. So we can train the machine to recognize that threat when it comes. But in situations like your zero-day exploits or zero-day threats, when we have no idea what the threat might look like, what the vulnerability might look like, you're going to need unsupervised learning from that. So it is very scalable and flexible for dynamic environments, detects anomalies without prior examples. Again, that's the whole point. It's basically going to train itself to the point where it can actually detect new kinds of threats never ever seen before. So example algorithms here would be your k-means, DB scan, and isolation forest. Now, when it comes to choosing whether to use supervised or unsupervised training, it's not that one is superior to the other. It all depends on what your data availability is, the threat visibility, and of course, your operational goals. So study this particular diagram very, very, very well. We have the comparison of supervised and unsupervised learning there. So study this very, very carefully. But let's talk about the model limitations that we have in security. This is the key security challenge. So it says, even the best trained ML models, they still carry risks that are inherent when deployed in the adversarial cybersecurity environment. So as security professionals, we must understand these limitations to avoid over-reliance. So the first one here, of course, is your historical data blind spots. Again, models that are trained on old kinds of data, old attack vectors, they will not be able to recognize new kinds of techniques that the bad guys, the cyber criminals and hackers are now using. And then this idea of concept drift, where real world data distributions shift over time. And of course, as the attack methods, the protocols, the tactics of attackers, as they evolve, a model's predictions may degrade silently without any obvious error signal until threats are missed entirely. So the whole idea of concept drift, you can think of it as a very slow degradation. Slowly but surely, it is becoming less and less reliable because the outside world is changing while its training, its data is still the same. It's not changing with the outside world. And then, of course, data poisoning. Sophisticated adversaries can deliberately manipulate training data to degrade model accuracy or create backdoors. Now, let's spend a little bit more time talking about the concept drift and data poisoning. You need to know these two really well for the exam. You're more than likely going to be asked questions in here. So these two threats to model integrity deserve special attention in any production security and deployment. So concept drift over time. Now, when attacker methods evolve, new kinds of attack protocols, new evasion techniques, the statistical relationship between input features and threat labels will change. So basically, a model that was trained 6 months or 3 months or 1 year ago may not be able to keep up with the new kinds of attack patterns that are being used today. So how can we mitigate this particular vulnerability? Well, obviously, we can implement continuous model retraining, right? And monitor detection rate metrics over time as key performance indicators. So we're going to make sure that we keep on training the AI models with new kinds of data, new kinds of information, and we also need to monitor the detection rate metrics over time to ensure that it's actually performing to a satisfactory standard. And then the data poisoning attack. So adversaries with any kind of access to the particular training pipeline, they can insert their own malicious data or corrupted data to poison the model. And it's especially dangerous in federated or crowdsourced threat intelligence models for obvious reasons. So the mitigation here is to use data provenance tracking. Make sure that whatever kind of data that's been used to train these AI models is actually legit and is free of any kind of corruption. And then, of course, adversarial robust testing before deployment. Now, going back to the isolation forest, here's an example of an algorithm that uses the unsupervised learning. It is a powerful unsupervised algorithm that excels at detecting outliers in high-dimensional security data, such as your network flow records, system call logs, or authentication events. Right there is the general process by which the isolation forest works. Basically, you're going to ingest logs from your firewalls, your intrusion detection systems, and so on. You're going to extract key features, run isolation forest to then flag any kinds of anomalies that might exist. So what they say here is that rather than profiling normal behavior explicitly, isolation forest isolates anomalies by randomly partitioning feature space. I want to give you an analogy to describe this, okay? Say, for example, you looked at the picture. It's a picture of 50 apples. They're all green apples, right? But there is a 51st fruit, which is a large pineapple in that same picture. So basically you have 50 apples and then 1 pineapple. Obviously, that one pineapple will stand out immediately because it's of a different shape. It's much bigger than the apples. So you will be able to detect that, oh, this is out of place instantly. That's pretty much how isolation first works. Rather than profiling normal behavior explicitly, it simply takes a look at what looks to be unusual or out of place and will immediately flag that. Let's delve a little bit deeper, okay? The real power of this particular kind of unsupervised algorithm, isolation first, it is when you merge it within an existing SOC tool chain. So as an example, take a look at this, okay? Step number one, we have the log ingestion. So again, your raw logs from your endpoints, firewalls, intrusion detection systems, network sensors, they will be streamed into a SIEM platform. Let's say Splunk as an example, right? Then comes feature extraction. So all these logs, there will be certain kinds of key features we need to look out for. Things like your connection duration, how long was a connection, the byte counts, right? Maybe in the organization, typically people don't transfer large amounts of data and so on, login frequency, things like that, right? And then comes the third process, model scoring. So in here, isolation first will score each event in near real time. Events with anomaly scores below a defined threshold will be flagged as potential threats. So as an example, isolation first believes that, okay, when it comes to the byte counts, the amount of data transferred in a particular log file, it shouldn't exceed 5 megabytes. Anything above 5 megabytes will be an anomaly. So it goes through the particular logs looking for that particular feature. It sees 2 megabytes, 2.2 megabytes, 3 megabytes. It now sees 7 megabytes. It knows instantly that, okay, this is out of the usual standard. So I'm going to flag this particular file because it has 7 megabytes in its byte count. So now comes the automated alerting. So flagged events like this particular one will be automatically escalated to analyst queues or trigger playbook-driven responses, reducing mean detection time significantly. So that's how the unsupervised algorithm could work in the real world. And of course, statistics do matter for security analysts. And why? Well, statistical learning goes beyond just raw accuracy, okay? It's not just about, oh, what decision or how accurate a particular model is. It's also understanding why the model made that particular prediction. Again, we've talked about how important this is, not just in cybersecurity, but in healthcare, in security, in pretty much any kind of field. So we need to understand why the model made that prediction, and then whether or not that prediction can actually be trusted in an adversarial context. 3 key features in here. First of all, the bias variance trade-off. We have the situations where the AI model can either have a very high bias where it basically underfits and misses threats. Maybe its scope or knowledge base of malware variants is very, very minimal. And because of this, it misses actual real malware variants. Or the exact opposite, which is now the high variance, where it thinks that, oh, any particular kind of file that has any particular kind of extension or this or that must be a malware variant. And because of that right now, it overfits. It will end up flooding analysts with your false positives. So security practitioners, we need to find the right balance between the high bias and high variance. And then the confidence intervals. So confidence intervals, they quantify uncertainty, helping analysts triage alerts by reliability, not just by raw score. The whole idea here is this, okay? The AI model or the ML model, when it makes a decision, when it flags a particular event as malicious, a particular log file as malicious, it needs to also state its level of confidence. If it flagged a particular file and said, okay, I have a 55% chance, I have a 55% level of confidence that this particular file is malicious, that will enable the actual human security analyst to take a look and say, okay, only 55%, let me do a human review. However, if the confidence level was, say, 95%, then in most cases, the human analyst will know that, okay, it's more than likely it is an actual malware or corrupted file, right? And then hypothesis testing. So in here, it asks, is an actual detected anomaly, is it actually significant, or is it just an anomaly that we can discard? It's nothing serious, it's nothing important. That's what hypothesis testing tries to answer. So these three key features, very, very important for statistics. So the key takeaways that you should know here for your exam objectives: number one, ML enables adaptive security. Again, you have ML models being able to learn data, recognize patterns, and then make decisions over time. You have your supervised and then your unsupervised training methods. So we can choose supervised learning for known labeled threat categories, and then use unsupervised techniques like isolation forest for anomaly detection in unlabeled high dimensional data. And then of course, models have adversarial attack surfaces. You have the concept drift, data poisoning. These are real threats. So security grade ML deployments require continuous monitoring, retraining, and input validation. And finally, statistical fluency is a non-negotiable. Interpreting the outputs made by the models, understanding the bias, variance, the confidence, and significance is a core analyst competency, not just an optional specialization. Thank you so much for watching. I will see you in the next class. Welcome back. Now let's talk about detecting suspicious activity with the use of machine learning. So this lesson is going to walk us through how large language models can be applied directly to security operations, from parsing raw log data to correlating multi-stage attack indicators in real time. So one of the objectives of the exam is that you should know exactly how to use AI in different kinds of scenarios. So we're going to explore them one by one. So large language models for security. Today, we have a whole bunch of them. However, I want you to understand there is a distinct difference between your cloud-based models, which are the very popular ones like your Claude, Gemini, ChatGPT, but we also have the local models, okay? Models like Mistral, as an example, V3, Llama. These kinds of models, the local models, they typically run entirely on the infrastructure within that particular organization. The data they work with never leaves that environment. So you would find this kind of local models typically in like security agencies, like, you know, the FBI, the CIA, NSA, those kind of agencies. And of course, it's very ideal for sensitive or regulated security data. Now, of course, your cloud-based models, the more popular ones, we train them on very large data sets. They have much higher reasoning and correlation capability, and they are, of course, best for complex and multi-stage analysis. Okay, so what makes a model more capable than the other, right? It all comes down to two main features. One will be the number of parameters with which the model can work with, and then second, and arguably more importantly, the data quality. I've talked about this several times already in this particular course. Data is like the lifeblood of any AI system. If you have high, good quality data, the AI model is going to excel. If you have biased or corrupted data, the AI model will not perform well. So the key insight here is that for security analysis, your model sophistication isn't just about the size, it's also about the data quality and domain relevance. Okay. Let's take a look at the very first scenario where we can analyze log data with AI, quite possibly the most common use of AI right now in cybersecurity. So raw security logs, they contain large amounts of data, we know that, but with the help of AI, we can dramatically reduce the time it will take to go through this particular log. So here is the recommendation. When you're working with AI, provide context, okay? Don't just copy and paste the security logs into the AI model and then say, hey, you know, do whatever you want to do, okay? You want to tell the AI exactly what it's working with, okay? What kind of data it is, and then what you're looking for. So for example, are you looking for data exfiltration, any sort of brute force attempts? Context will dramatically improve the quality of the output made by the AI. We should also understand there is a difference between your basic and advanced pattern recognition. I will give you an example of this in the next slide. And then iterative refinement. So you want to start with broad questions like what looks suspicious? And then when you get the output, you can begin to drill further and become more specific. You can ask questions like, okay, explain the relationship between these three events, or be a bit more specific in what you are looking for. So take a look at this, okay? Advanced models like your ChatGPT 4.0, they have the ability to not just flag events, but also correlate multiple log entries. This is extremely powerful, and you're going to see why in just a moment. Take a look at these events that occurred, okay? First of all, we had somebody uploading a file, a malicious file, and then roughly around the same time, there was a suspicious connection request to an outbound destination. Now, in this kind of scenario, ChatGPT or any advanced AI model has the ability to recognize that, this particular event of the file upload, it must be related to this other suspicious event where we have an outbound connection request. So this particular type of multi-stage reasoning is what separates advanced models from the basic ones. And that saves analysts, of course, critical response time during active incidents. Now, this is very, very important. Correlation is very, very important because guess what? 76% of breaches span multiple systems. Very hardly will you ever hear of a cyber attack that involves targeting just one particular system or one particular network. It's typically lots of networks, lots of systems, okay, all at the same time. And without AI, it could take 287 days on average to identify a breach. So correlation is very, very important. AI acts as a force multiplier. It can ingest all relevant context simultaneously and surfacing the narrative hidden within the noise. This will save analysts plenty of time, reduce their fatigue, and then surfaces attack intent, not just raw events. So comparing model capabilities, all right, you want to choose a model based on what it is you're trying to achieve. So for your basic or local models, these are great for flagging individual suspicious events. They're good for pattern matching on known signatures, best when data cannot leave or should not leave the network. Know this for the exam. Examples are your Mistral and your Phi3 Mini. Now, your advanced models, they understand relationships between events, correlation. So they can infer an attacker's intent or technique, best for complex multiple source investigations, and of course, your examples, ChatGPT, Gemini, Claude, and so on. So your decision rule is this. If data contains your PII, your personally identifiable information, PHI, or classified content, use a local model. Again, if you're dealing with very sensitive, important data, you want to go with the local models. Now, if your analysis involves complex attack reconstruction, you want to use a cloud model on sanitized or non-sensitive data. Let's take a look at a practical security use cases, okay? And of course, LLMs are already being applied in security operations today. But look at this, okay? All in action, the 4 core use cases. The very first one here is your vulnerability scan prioritization. So we can feed a raw scan output, maybe from Nessus or OpenVAS, into an LLM, and then we can say, hey, what are the top 3 critical vulnerabilities I should patch first? So in this particular kind of scenario, the model can factor in the CVS scores, exploitability, and asset context to produce an actionable ranked list. Of course, this will save you plenty of time. And then, of course, CVE identification in logs. You can provide your favorite AI model, the system logs, and then ask it to identify which CVEs may be actively exploited in your environment. We also have the multi-source incident summary. So basically, when an incident involves data from alerts, endpoint telemetry, your LLM can actually synthesize all sources into a coherent incident narrative, dramatically accelerating your post-incident reporting as well as the root cause analysis, and of course your interactive threat Q&A. You can actually have a chat with your AI model about threats. So rather than manually reading through your large scan files, analysts such as yourself, you can ask your AI models like, hey, are there any unauthenticated remote code execution vulnerabilities in this report? So basically, you can have a conversation with your AI model about security threats. So here is a hands-on demo that was provided by CompTIA, a sample prompting strategy. In this scenario right here, we have uploaded the log data from our database. It could be from maybe a firewall, Apache, Windows, you name it. And then look at the prompt, okay? We're saying, please, number one, identify any suspicious or anomalous activity, note the relationship between related events, flag any indicators of IOCs, summarize your findings either as critical, high, medium, or low, and then recommend immediate response actions. And then after that, we then paste the log data. So here's an example of a really good prompt because again, we're telling the AI model what we're working with. I am providing you with Apache logs. We're asking the AI model what to look for, identify any suspicious or anomalous activity, and then check to see if there are any relationships, flag any IOCs, summarize the findings, and then recommend immediate response action. So we're providing plenty of context to the AI model. So key takeaways for this particular lesson: choose your model wisely, okay? Cloud models, local models, it all depends on what you're looking for, what you're working with. Context is everything, context is king. Correlation over isolation. Advanced models, they shine best when correlation is important. And then AI accelerates analysts' decide. Okay, so AI helps us make the decisions a lot quicker, but at the end of the day, we're still the ones who will make the final decision, at least for the time being. And that's pretty much it. So join me in the very next class. I will see you then. Cheers. Let's now take a look at transformers in cybersecurity. What exactly are they? Well, they are a class of neural network architecture designed specifically to process and analyze sequences of data, most notably human language. So the thing is, earlier AI models that didn't work with transformers, what they would do is if you provided them with a sentence, say, I am going to the market, they would read that entire sentence word by word. I am going to the market. Obviously, this wasn't very effective and was also quite slow. However, what transformers do is that they will evaluate all parts of a sequence simultaneously, enabling them to understand nuanced context. So the thing is, instead of reading the entire sentence word by word with transformers, the AI model will simply see I going market. It knows, okay, it knows the context. Okay, this person is telling me they're going to the market. They don't need to take a look at the words like to, the. All those words will be ignored. That's the power of transformers. And of course, transformers are used heavily in natural language processing, which we'll talk about next. So transformers excel at identifying relationships between distant pieces of information. For example, how a word at the start of a sentence modifies the meaning of a word at the end. That's the ability of transformers. So this capability and ability makes them uniquely powerful for understanding intent, context, and subtle patterns in text. So we've talked about this earlier. This was basically a breakthrough, a vital breakthrough in AI development. So they underpin virtually every modern NLP breakthrough: translation, summarization, text classification, as well as question answering. So there is a secret weapon deployed by transformers. It's called the attention mechanism. What exactly is this? At the heart of every transformer, we have the self-attention mechanism. It is a mathematical process that assigns relevant scores between every token in a sequence. So this would allow the model to focus or concentrate on the most important relationships, regardless of how far apart they appear in the data. So with self-attention mechanism, we have parallel processing. Basically, your transformers, they analyze entire sequences at once and not word by word. They're also able to provide context. They have contextual understanding. So each token's meaning is computed in relation to all other tokens, allowing the model to capture nuance, context-sensitive semantics. So again, in that sentence, I am going to the market. Each word will be a token. And then depending on the relevance of the particular word, the token could have a high score or a low score. So the words like am, to, they will have very, very little scores. But however, I, going, market will have the much higher relevance scores. So scalability, transformer architectures scale effectively with more data and compute, which is why they form the backbone of modern LLMs like GPT and BERT. Now, transformers specifically in cybersecurity, we use them for threat report analysis, phishing detection, incident response automation, as well as UEBA enhancement. Pretty much the exact same thing we use NLP for. And then security applications deep dive. Okay. With the use of transformers, we can use them in log parsing and threat detection. So security environments, we know they produce millions of log entries on a daily basis. Logs from firewalls, anti-malware, your IDP, and so on. So these transformers can parse large volumes of raw text logs, classify entries by risk level or levels of criticality, and then surface anomalies that traditional SIM rules would miss, all without rigid signature matching. Also in malicious content classification, because transformers have the ability to learn semantic patterns associated with malware, ransomware, and so, they can classify content as malicious with high accuracy, and then suspicious email patterns, all right? Beyond simple keyword matching, transformers evaluate the structural and semantic patterns of emails to identify business email compromise, spear phishing, lateral phishing, whale phishing, and all other forms of phishing. But we can also use transformers for insider threat identification. Basically, transformers can analyze sequences of employee communications and behavior signals over time, identifying subtle linguistic and behavioral indicators of insider threat. We're going to talk about this a lot more in the upcoming lesson, so stay tuned for that. So from transformers to LLMs, the foundation, every major language model today, your GPTs, Claude, Gemini, and so on, they are built on the transformer architecture. And understanding transformers is therefore a foundational, or rather it's foundational to understanding how modern Gen AI security tools function, as well as where their limitations lie. So for security practitioners, this lineage matters. The same architecture that powers a customer chatbot also underlines AI-assisted threat hunting, automated report generation, as well as intelligent SIEM enrichment tools assessed on the CompTIA exam. All right, so why do transformers matter for security scale? Well, we do have what we call the unstructured data problem. Again, the vast majority of security data we get from firewalls and IDPs and so on, they are typically unstructured. Traditional signature-based tools cannot process this data meaningfully. They need the data to actually be structured in the first place. Now, transformers, again, with the help of NLP, which we'll talk about later, they are able to bridge the gap between human language and machine understanding. So this, of course, leads to speed of scaling as well as coverage, because a transformer-based pipeline can analyze thousands of log entries or communications per second, providing continuous, always-on monitoring that augments the SOC without replacing the critical thinking of the human analyst. So some key takeaways: Transformers, they bridge the human language and machine understanding. They're critical for processing unstructured security data at scale. And of course, they serve as the foundation for all your modern LLMs and Gen AI security tools. Now, the major exam tip here, be prepared to explain how transformers will differ from earlier RNN LSTM architectures, why attention mechanisms will improve context understanding, and how they underpin Gen AI tools referenced throughout the SecAI Plus objectives. Thank you for watching. I'll see you in the next class. Let's now move on to a subset of machine learning, which is of course going to be deep learning. Now, what exactly is deep learning? Well, like I said, it is a specialized subset of machine learning that actually uses multi-layered neural networks to automatically discover new and complex patterns in data without being explicitly programmed with any kinds of rules. That is the key advantage of deep learning. So it uses multi-layered networks. They're basically a series of interconnected nodes that will process data at increasing levels of abstraction. One of the core advantages of deep learning over ML is that ML will typically struggle with unstructured data. Right? ML works best when the data is actually structured, but when you have your unstructured data like images, audio, free from text, it will struggle, but deep learning will excel at processing those kinds of data. So core applications, we use deep learning for image recognition, speech processing, as well as natural language understanding. Now, specifically in cybersecurity, we use deep learning for large dataset analysis, malware classification, APT detection, advanced persistent threats, and then of course in IDS support. These are just a few of the many ways how we use deep learning in cybersecurity. Now, comparing deep learning with your traditional IDS, your intrusion detection system, typically the traditional IDS, you have to program the rules explicitly into its system, okay? So your traditional IDS will depend heavily on manually defined signatures and heuristics. Now, this is very effective when the threats are known. When you have a whole database of different kinds of threats, their extensions, things like that, you can easily tell the IDS, your traditional IDS, to look for these kinds of things. But what happens when the threats are unknown? That's when your traditional IDS will fail. But with deep learning, it learns directly from raw, unlabeled data, no rule writing required. So it continuously adapts as new kinds of threat data will flow in. And because of this, it has the ability to detect zero-day attacks and unknown attack patterns automatically. So key point here, deep learning IDS can detect novel attack vectors that signature-based systems will always miss. And this is a critical advantage in a rapidly evolving threat landscape. Okay, now let's talk about the architectures involved in deep learning. Now, of course, selecting the right kind of architecture is the key to building very effective AI-powered security tools. So we do have your CNNs, your convolutional neural networks. Now, these kinds of architectures, they were originally designed for image recognition, but it turns out that they are actually highly effective at being able to analyze raw byte sequences of executable files. And because of this, they are a great choice for any kind of malware classification or even a threat classification. We have the recurrent neural networks, your RNNs. Now, these are built to process sequential data and time series data. And because of this, they are great at analyzing security logs. Think of them as being able to connect one security log to another. Remember, we talked about this in an earlier lesson where we had the file upload, and then after the file upload, we had a illegitimate connection request, okay? That ability of the AI to be able to match both particular events together, it's because of RNN. So they will be ideal for analyzing security logs, network session data, and things like that. But we also have the autoencoders. What exactly are these? Well, unsupervised networks are trained to compress and reconstruct what we would call normal data. Now, when an input will deviate significantly from the learned norms, when an anomaly occurs, okay, the reconstruction error will spike, flagging it as a potential anomaly or intrusion. That's basically how autoencoders work. So with all of that in mind, these are the base cases where we can use these kinds of architectures. So for your CNN, spatial pattern recognition in fixed size output. So because of this, it's going to be great for malware classification. Your RNNs will be great for log analysis, network session sequencing, because they are good at sequential and time-ordered data processing. And then your autoencoders, they are best for unsupervised anomaly detection. And because of this, they will be best used for flagging deviations from baseline behavior. Please know these three, what they're best for, and the security use case for the exam. So each architecture will address a distinct challenge in security data analysis. So when you know what you're looking for, you can go with the best architecture for that particular case. Now, security use cases, of course, deep learning has been deployed across a wide range of real-world security scenarios. We have in network traffic analysis, malware classification, and of course, in behavioral analysis. So with deep learning, we are continuously improving our ability to defend against threats. For example, unlike static rule-based tools, your deep learning models will actually grow stronger over time. Think of them as becoming more and more experienced, right? The more data they're exposed to, the more kinds of threats they're exposed to, the better they will become at detecting those threats. So every new threat data point, whether it's a malware, attack log, network trace, will become its training material that will refine its detection accuracy. So again, with experience, with time, they only get better and better and better. So the continuous learning advantage here is that new malware samples will expand the training dataset automatically. Detection rates will improve with each retraining cycle. Models can be fine-tuned for specific kinds of environments or threat profiles. And of course, it will reduce the detection gap between emerging threats and security response. So key takeaways from this lesson: number one, your deep learning is basically the same thing as your multi-layered pattern recognition. They will learn complex representations from raw, unstructured data without manual feature engineering. Always remember, deep learning, unstructured data. Deep learning, unstructured data. Structured data, machine learning, all right? Three core architectures: your autoencoders, your CNNs, your RNNs. Know what they are, know the best cases for them. It will always outperform traditional IDS, and of course, DL, deep learning, has been used in broad security applications. Thank you so much for watching. Of course, I will see you in the next class. Let's now talk about NLP in cybersecurity, and that's of course natural language processing. And it's basically the branch of AI that would allow computers and AI models to understand, interpret, and generate human language, essentially bridging the gap between machines and natural communication. The fact that we can have a friendly chat with Claude or with ChatGPT, it's all down to NLP. So NLP allows AI models to parse syntax, semantics, and then of course generate context from raw text. Interpret, they can derive intent and meaning from unstructured input, and of course generate, they can produce coherent, contextually relevant language output. So NLP specifically in cybersecurity has many use cases. We can use NLP in threat intelligence, for extracting IOCs, your indicators of compromise from reports, for detecting phishing, and of course for also automating responses. Now we do have this common SOC integration patterns with NLP, where with the use of RAG, the retrieval augmented generation, where the AI model can look up an external source for more information on a particular topic or subject, we're able to integrate them with your tickets, run books and so on. So basically, your AI model right now can look up threat intelligence reports, playbooks, things like that to generate more information about a particular kind of malware or file or threat report. So modern NLP deployments don't operate in isolation. Instead, they connect directly into existing security tooling via structured output formats and API integrations. And just like I said, you have the ability of your AI models to use RAG to go over run books. They can retrieve relevant context before generating their own response. Of course, JSON structured outputs, these are very, very important because a lot of tools like your SOA, your SIM, Splunk, and so on, they tend to use structured outputs that are in the JSON format. We're going to talk more about this in the system prompt class. And then function calling, direct invocation of SIM queries, SOA playbooks, and TIP lookups. These are all the things that AI models can use because of NLP. Now, in action, of course, with NLP, AI models, they can group and classify high volume security alerts to reduce analyst fatigue. Obviously, because of NLP, the AI models can recognize the kinds of threats that are out there and put them in respective categories. Of course, they can monitor the dark web to identify any new kinds of threats that might be on the horizon. And of course, the ability to extract IOCs from reports. Now, we do have guardrails, of course, for safe NLP deployment. So high capability models will introduce new kinds of risks, such as hallucination and prompt injection. And these are top concerns for security contexts. So to enable some safeguards, we can do things like, of course, filtering our inputs. So basically, we have to sanitize and validate prompts before model inference. Audit logging, we want to maintain full traceability of model inputs and outputs. And of course, also filter the outputs. Screen generated responses for unsafe or incorrect content. And of course, human in the loop. High-risk actions will require an analyst's approval before execution. These are some of the safeguard rails for NLP deployment. Now, specifically for the exam, you need to be aware of LLMs and SLMs, your large language models and your small language models. Just because the large language model is typically much more powerful, stronger, more effective than the SLM, your small language model, it doesn't mean they're always the best choice for every kind of scenario. So what I want to show you here basically is when to use your LLM and when to use your SLM. Now, your large language models, these are great for threat intel summarization, creating different kinds of playbooks, and of course for your conversational security bots. However, because they are very large and they're very, very effective, they're very advanced, sophisticated, they require massive computing power. So they can use tens to hundreds of billions of parameters, require up to 40 or 80 gigabytes of RAM, and multiple high memory GPUs, your graphics processing units, not just your CPUs or central processing units. So LLMs can be weaponized to craft convincing phishing emails and also social engineering scripts. Basically, a dual use risk SOC teams must account for. They must be well aware that LLMs can be used by both the good guys and the bad guys. Now, your SLM, your small language models, they are very efficient, of course, by design specifically. They're built for speed, efficiency, and local deployment. And they're typically the right choice when latency and resource constraints matter. So yes, they're not quite as powerful as your large language models, but they require far less computing power. They don't even need GPUs. Basically, they can run on your everyday CPUs. One single GPU can accelerate its performance a lot. 1 to 8 billion parameters. And they're optimized for on-site deployment. Basically, these are the kinds of models you can run locally within your premises. You don't have to deploy them on the cloud. So obviously lower cost, lower latency, stronger data privacy posture. So they're perfect for log analysis, alert classification, and of course for flagging anomalies. You should also be aware for the exam of this deep learning model we call the GANs, your generative adversarial networks. Now, these typically have two neural networks. First of all, you'll have the generator. These are used to create synthetic data. And then you'll have your discriminator that will then attempt to distinguish the synthetic data, aka the AI generated data, from what's actually real. So we can use GANs basically for image synthesis. They can generate photorealistic visuals, data augmentation. Of course, they can expand the training data sets because now we can create synthetic data that looks very, very realistic. And of course, we can craft scenarios that will look like realistic adversarial environments. So in cybersecurity specifically, we can use GANs for synthetic threat scenarios where we can generate realistic attack simulations either for training or stress testing detection systems, for synthetic log generation, for malware variant generation as well, and of course, for privacy safe data sharing. These are just some of the examples where we can use GANs in cybersecurity. So your key takeaways: NLP unlocks unstructured data. Because of NLP, AI models are able to work with data that isn't structured. They can match model skill to the task. So basically, you must match the kinds of models you're working with to the task. Again, just because an LLM is significantly more powerful than an SLM, it doesn't always mean that LLMs are the right choice for every kind of task. And then guardrails are non-negotiable, okay? Guardrails, security, privacy, these typically should be requirements and not just options, okay? And then GANs strengthen detection models. Synthetic threat data generated by GANs enable robust training, red team exercises, and privacy compliant research collaboration. Thank you for watching. I will see you in the next class. Let's now move on to the very next section, section 3. And here we're talking about AI model training and prompt engineering. So you've learned already about the basics of AI, but now let's talk about how AI models are actually built, how we train them, and also how we as security professionals, we can actually shape, use, and protect the entire process. So you're going to learn exactly the differences between the supervised learning and unsupervised learning. You will learn about federated learning, reinforcement learning, and why, of course, each matters in the cybersecurity context. And then also prompt engineering for security. You're going to learn about user prompts, system prompts, what the differences are, and also how you can craft really effective prompts. And then also securing the model. Whenever we're training AI models, vulnerabilities can exist even at that stage. So you're going to learn how you can protect the AI model from any kind of infection. So by the end of this section, you will learn how to speak the language of AI and how to make sure it actually works for security and not just against it. Let's get to it. Welcome to the brand new module where we're taking a look at AI model training. And over here, we're going to analyze the different ways how our AI models can be trained. So AI in modern security operations. AI-driven security platforms have fundamentally, of course, changed the scale and the speed of threat detection. And that's because AI models, they can ingest and process a huge ton of different kinds of data, whether it's network packets, DNS queries, your endpoint logs, your scan reports, and so on, and then correlate observations across millions of signals simultaneously, clustering unknown executables into emerging malware families and autonomously updating intrusion prevention policies in near real time. So AI in your modern security operations, it's very, very fast, can be scaled, but unfortunately, you also have the dual role where your machine learning systems are defendants, but also targets, and compromising the model will compromise the defense. So basically, if we are able to compromise or corrupt the AI model, well, we are going to end up compromising whatever kind of defense that particular model was designed to produce. Now, key AI model training concepts. Every security model, every AI security model is only going to be as strong as the data it learns from. I've talked about this several times already in this course. Data is the lifeblood of AI development. not all data is equal in quality. The more quality and the more volume of data the AI model is trained on, the better it will become. However, the training pipeline from raw data ingestion to learn decision boundaries is where model quality is determined. Now, the training data, of course, is the foundation of model accuracy and reliability. And of course, garbage in will give you garbage out. If you trained your AI models with biased data, it's going to give you biased results. So diversity will ensure generalization across novel attack variants. The kinds of data, apart from being high quality, they also need to be very diverse when training the AI models. So we've talked about this. We have supervised learning, where models will learn from labeled examples. For example, this particular file is, this particular email is spam. This particular email is legitimate, something like that. And then unsupervised learning, model will discover on its own hidden patterns or complex patterns in unlabeled data. And of course, these are useful for your zero-day threat detections and anomaly detections as well. We've talked about the concepts of overfitting and concept drift. Overfitting is where your AI model, instead of learning the ability to recognize pattern on its own, it simply memorizes the training data. The best analogy I can give for overfitting is, remember when you were in high school, or at least I remember when I was in high school, we had certain kinds of students who, in order to pass an exam on a particular kind of subject, they would cram the entire textbook for that particular topic, right? And of course, they will do very, very well because the questions in the exam are taken specifically from that textbook. And because they've memorized everything, they are able to pass the exam. However, they don't really understand the topic itself. So if they ended up being asked a question or anything that isn't in that particular textbook, they end up messing up. That's basically what overfitting is. The AI model just simply memorizes all the training data, but it doesn't actually develop the ability to learn on its own. That's basically what overfitting is. Now, we can solve this issue by the concept of data set separation, where we will have different kinds of data sets to train the data at different stages. So we'll have your normal training, validation, and then the test data sets to test whether or not this AI model can actually think on its own. So each split will serve a distinct purpose and must never overlap or contaminate the others. We need to keep these data sets separate from one another. And then concept drift. We've talked about this also, where an AI model, it relies solely on its trained data, but because the outside world, the threats are changing, there are new kinds of threat methods and attack methods, but because the AI model isn't updated, eventually with time, it becomes pretty useless at detecting these kinds of threats. So how we can solve this is through cross-validation, evaluate the model performance across multiple data splits to produce statistically sound results, and eliminate bias introduced by a single lucky or unlucky partition. Now, this is your training pipeline. So training, validation, and then test. So strict separation of these three data set roles is the cornerstone of sound machine learning security engineering. There should never be any kind of communication or contamination across these data sets. This brings us to the data poisoning attacks. What exactly is this? Among the most insidious threats to ML-based security systems, data poisoning targets the training pipeline itself. Think of this as kind of like the insider threats for machine learning training, long before the model even reaches production. So adversaries subtly manipulate training samples to embed hidden vulnerabilities, backdoors, or decision boundary distortions. Now, as I'm reading this, I just thought of something very, very, very funny, okay? I don't know whether you've seen this movie called RoboCop, the old one that came out in 1986 or 87. If you haven't, maybe you want to watch it, maybe you don't. It doesn't matter, okay? What the movie is about is basically a policeman that was killed, and they ended up turning him into a police robot. How do I describe this? A machine, a police robot, basically. Okay, he's a robot but acts as a police officer, right? Now, when it was being developed, when it was being built, he originally was programmed with three directives. Okay, serve the public trust, protect the innocent, and then uphold the law. Those were the three prime directives this Robocop was supposed to act upon. However, one of the bad guys in the movie, because he was in a very senior position within the company, he was able to inject a fourth directive that pretty much prevented Robocop from arresting him later on in the movie. So, spoiler alert. Whatever, okay? Watch this.
What are your prime directives?
Serve the public trust, protect the innocent, uphold the law.
That's good. That's very good. Huh? Huh? What's the matter, officer? I'll tell you what's the matter. It's a little insurance policy called Directive 4. My little contribution to your psychological profile.
All right, so welcome back. So did you see that Directive 4, classified? That was the injection of this new directive that prevented Robocop from arresting that guy later on in the movie. So that's basically a data poisoning attack where you go after the training data with which the machine model is being trained on. So in many cases, it's a silent manipulation where the poison samples are crafted to look very legitimate, or it's very, very small little changes that will be very, very hard to detect. And then dataset separation as a defense. So what we want to do here to prevent this kind of attack is that we want to separate validation and test sets, which will provide a clear independent signal to detect performance degradation, distribution anomalies, or covert manipulation before deployment. So early detection imperative is very, very, very important. Catching degradation or manipulation before production is critical. Before we start producing the AI model en masse, we need to make sure that we've detected any kind of data poisoning attacks. And because of this, red team exercises are a very, very popular team for ML security. So traditional red team will test human and network defenses. ML red team extends this to test AI models themselves. So you'll have things like injecting outlier and poison samples into the training data. It will simulate adversarial inputs at inference time, test model behavior under distribution shift, validate that decision logic resists manipulation, and then confirm that the model is reliable for automated detection and response pipeline. So the whole idea behind red team exercises for ML security is to test not just the accuracy of the model, but its resilience, its ability to resist being manipulated or contaminated. So production model integrity, 4 major stages. Training integrity, we want to make sure the training has the integrity. The validation integrity as well. Deployment integrity. And then, of course, continuous monitoring. These are the 4 key parts of the security lifecycle of the production of an AI model. We need integrity at all these 4 stages. So the dual role of security teams. Modern cybersecurity professionals operating in AI augmented environments must develop ML expertise alongside traditional security skills. So there you have your traditional defender, your ML security specialist, and then you have the overlap, such as understanding ML attack surfaces, red teaming models, securing automated response pipeline. So please study this. It's going to be very, very important for the exam. So your key takeaways: data quality is, of course, security. Separate your data sets. Poisoning is silent. Red team your models and make sure you have integrity at every single stage. And the exam tip: be prepared to identify overfitting versus concept-driven scenarios, explain dataset separation strategies, and describe how data poisoning attacks differ from your traditional network layer intrusions. Thank you for watching. I will see you in the next class. All right, so let's take a look at the very first type of training in here, and that's going to be supervised learning. So the core idea behind supervised learning is that the models, they will be trained on labeled data. Take, for example, you're trying to train a spam filter. the model will be trained on what is spam and what isn't spam. So in security contexts, that means feeding the model archives of events flagged either as benign or malicious so that it will be able to learn to distinguish them automatically. So as an example, we will have the benign data. This would be your normal login events, standard process launches, and so on. And then malicious would be like your PowerShell obfuscation, phishing URLs, and so on. So once trained, the model applies these learned patterns to real-time analytics engines, flagging suspicious activity as they occur across the network. Now, when it comes to supervised learning, there are two major algorithms you need to be aware of. Now, things can get pretty technical in here in the explanation. All you need to know for the exam is this. First of all, the first type of algorithm would be the gradient boosted decision trees. These algorithms, they allow the model to be trained sequentially. Basically, each tree will correct the mistakes of the previous one. And because of this, they are great for detecting suspicious PowerShell and phishing domains. They can flag lateral movements easily and also supports vulnerability prioritization workflows. The second algorithm are your CNNs, your convolutional neural networks. These have the ability to analyze raw byte sequences, and because of this ability, they are great for detecting malware variants. They can learn spatial patterns within executable structure and effective against packed and polymorphic malware. So for the exam, all you need to know is gradient boosted trees, sequential training. The tree corrects the errors of the one before it. And because of this, they can detect suspicious PowerShell commands, flag lateral movements, support vulnerability prioritization workflows. Your CNNs, they analyze raw byte sequences. And because of that, they are great for detecting variants, malware variants, polymorphic malware, and of course, learn spatial patterns within executable structure. Now, there is something known as the decision boundary. How these models are able to indicate whether an activity is benign or malicious is by the decision boundary. Once that boundary has been crossed, that's when the model will say, okay, this is an anomaly, this is a malicious event. So it is a trained model will draw the decision boundary to separate benign activity from malicious activity in feature space. Now, where this boundary sits will determine your rates of either false positives or false negatives. Now, it's also very important to understand that within security or pretty much any sensitive domain, whether it's in the medical field, security, criminal investigations, explainability is not optional. In other words, we need to be able to understand why the AI model made a certain kind of decision. We just can't say, oh, well, it flagged this particular event. We don't know why, but hey, we're just going to go with it. That doesn't work. Every single event, every single anomaly that the AI model flags, we need to understand why the model made that decision in the first place. So without clear explanations, triage will become guesswork and escalation paths will break down. Now, there are two ways how we can go about this. Okay, we can either use gradient boosted trees. What gradient boosted trees do is that they typically, their prediction levels are not going to be as good, or I'm sorry, their accuracy levels are not going to be as good as deep neural networks. However, gradient boosted trees are much easier to understand why they made the decision because they attach something known as the feature importance scores. Let me give you an example, okay? Let's say you have an AI model that's meant to track network traffic, okay? But then it flags an event, it flags a connection request as an anomaly. If you're using gradient boosted trees, it will say something like, oh, I flagged this particular connection as an anomaly because, first of all, the connection request time was at 1 a.m., which is very, very unusual. So it might say, okay, I gave this a score of 55% importance. The second feature here is that the connection was made from a mobile device, which is also unusual. I'm going to give that one a score of 25% and so on. So because of these scores, the analyst will be able to see why the AI model flagged that event as being malicious or as an anomaly. Now, deep neural networks, these tend to be very, very, very accurate, more accurate than gradient boosted trees. The trade-off, though, is that with your deep neural networks, being able to explain why they made those decisions can be very, very difficult. They have this opaque problem. So the best practice is when necessary or when needed, we can combine these advanced models, these deep neural networks, with something that we call the sharp values. Sharp values basically help to explain why your deep neural networks made certain kinds of decisions, or we could also use rule-based explanations for analyst-facing alerts. So we can use the rule-based, like, okay, if this connection is made between this IP address and that IP address, flag it as potentially malicious. If this connection request is made to this server, flag it as malicious, and so on. So basically handwritten rules. Now, there is this thing called weak supervision, which you should be aware of for supervised learning. Imagine you trying to train an AI model on millions of labels. It will be impractical to be able to label over 1 million different things. So this is where weak supervision comes into play. So weak supervision can actually automate this labeling process by simply using existing knowledge sources to tag raw data at scale. Now, how does it work? We have the auto tags raw logs using threat intelligence feeds. So the AI model can simply pull in the tags and labels from threat intelligence feeds, your Yara Sigma rules, and so on. However, we do have the risk of the label noise, where with automated tagging, we might introduce inaccurate or conflicting labels. Imagine the AI model pulling its information or labels from 3 different threat fields, but then these threat fields, these threat sources, they have different interpretations or different scores for a particular kind of threat. Which one is the model supposed to trust? That's where you have this risk noise vulnerability. So the security consequences here are that label noise can lead to false positives, basically innocent or benign events being flagged as malicious, or false negatives where actual attacks are missed entirely, which is by far the most dangerous outcome. So how do we handle the label noise? There's 4 ways. First is noise robust loss functions. Basically, we can modify the objective of the training to reduce the influence that mislabeled samples may actually have. And we can do this through confident learning, algorithmically identify and correct suspect labels by comparing model confidence against assigned tags. And then we can automatically flag any likely annotation errors. How do we do this confident learning? Well, we do so through cross-source validation. If you have a particular kind of tag that appears in multiple sources, in multiple feeds, and it's the same, it's pretty much consistent, then we can assign plenty of confidence towards that particular tag. We know that, okay, this particular tag has been verified by multiple sources, it must be good. But in a situation where a tag appears in only just one particular intel source, the confidence levels may not be as high, and as such, the model can flag those kinds of labels for human review. So, active learning, the model flags its most uncertain samples for human review, directing analyst effort where it matters the most, and maximizing label quality efficiently. Now, very important for the exam, I want to show you the workflow for supervised learning. There's basically 5 stages: collect and label, pre-process, train, evaluate, and then interpret. We're going to walk through each step very, very soon, but know that in each step introduces different types of vulnerabilities, okay? You can have issues with mislabeled data, poor normalization, overfitting, or misread evaluation metrics. Mastering this workflow means knowing where things will go wrong, not just when they go right. Okay, let's start with steps 1 and 2, collect, label, and preprocess. Let's say we're trying to train an AI model on being able to detect attacks on a network. The very first thing we're going to do is we're going to collect the data set. Now, there is an actual real live data set called the UNSW NB15. Unless I'm mistaken, I think it's originally from Australia. Basically, it's a massive data set of about 9 to 10 different types of attacks on networks. So things like your reconnaissance, exploits, DDoS attacks, and so on. It's all contained in this particular data set. And that data set also has many samples of what normal traffic looks like. So that data set already has the labels for the AI model. The AI model knows what is normal and what particular kinds of traffic might be under reconnaissance, DOS, exploit. It's all been done already. So we're going to take that data set, dump it into our AI model. Okay. Next comes the pre-processing steps. What exactly is this? If you're exposing an AI model or this particular AI model to actual network logs, sometimes it can be very difficult for the AI model to understand what's actually written in those logs. Remember that AI models are binary. They think of zeros and ones. So when you begin having in your actual network log before, you may have issues like certain kinds of fields with protocol names in it like UDP, TCP, HTTP, SMTP. The AI model doesn't know what is this. So we're going to have to convert these kinds of fields into binary columns so that the AI model understands what it's looking at. It's called the one-hot encode categoricals. Also, you may have certain kinds of columns like your source bytes. Basically, this is the column indicating how many bytes were sent by the source workstation. In some cases, it could be 50 bytes. In other cases, it could be, 500,000 bytes. Now, we don't want those kinds of very large numbers or large values to dominate the signal for the AI model. So therefore, we'll have to normalize them. Now, how can we normalize them? We can turn them into fractions. So 50 can become 0.005. 500,000 could become maybe 50 or 500. So that is still within a normal range rather than having 50 and then 500,000. So that's where normalizing numerics comes into play. So basically, we are preparing the network traffic, the network logs for the AI model to understand what it is looking at. So we have the training data. It now understands the network logs. Next comes the training and evaluation stages. So we're going to train the model, feed a gradient boosted tree classifier on the labeled training set. The algorithm will build trees sequentially with each iteration reducing residual errors from the previous round. However, very important, always split your data. The actual training set, your data for training should be different from the one for testing how well the machine is actually performing. It's not going to make any sense if you expose your AI model to the data sets meant to test its ability. It's kind of like you trying to test a student's knowledge of a particular topic on an exam, right? But the student has already seen those questions to the exam. It doesn't make any sense at that point, right? So that's why it's very important to separate your actual training data sets from the data sets you use for testing the efficiency of the AI model. So there's two evaluation metrics. One is the precision, okay? Precision basically identifies of all the flagged events, how many were actually malicious. You flagged all these anomalies, okay, but how many of them were actual malicious? So low precision means alert fatigue. So you're gonna have plenty of false positives. So many events, so many files that were classified as flagged or as anomalies when they were benign. Or recall. Of all malicious events, how many were actually caught? Low recall means missed attacks. And when we find the mean, the harmonic mean of your precision and recall, the average basically, that will give the F1 score, which is basically the balanced summary metric for detection quality. So the F1 score will determine the detection capabilities of the AI model. And then finally, step 5, interpret the confusion matrix. So the confusion matrix breaks down every prediction into 4 categories, okay? These are the 4 categories right here: your true positive, false positive, false negative, and then true negative. Obviously, the best category would be the true positive, where the AI model flagged a malicious event and it was actually malicious. The absolute worst category would be the false negative, where the AI model completely missed an actual real malicious event or malicious file. So in security, false negatives are catastrophic. A missed intrusion can mean undetected data exfiltration for weeks. And analysts must consciously choose where that balance is based on their threat model. Basically, they're going to have to tune the decision threshold, shift the model toward higher recall at the cost of more false positives, or vice versa. Okay, so the relevance to your SIEMs and XDR platforms, all the SIEMs that you've ever worked with or that you know of, Splunk and so on, you name them, they all use the 5-step workflow. So for things like raw telemetry ingestion, your network flows, process logs, and authentication records are basically the labeled data sets of production systems, continuously updated with new threat intelligence. Your real-time detection logic, so your vendor machine learning engines will apply trained models to streaming telemetry, generating alerts with confidence scores, the output of their internal evaluate and interpret stages, and of course, the analyst empowerment. Understanding the pipeline lets you fine-tune detection thresholds, interpret the model-driven alerts critically, and of course, you'll end up reducing the false positive rates rather than treating the platform as a black box. Okay, so the major key takeaways: labeled data is, of course, the foundation of supervised learning. Trees and your CNNs will dominate. Okay, so gradient boosted trees will handle structured telemetry with explainability. Your CNNs will analyze raw bytes to catch signature evading malware. Weak supervision scales, but with risk. So again, remember, weak supervision isn't all bad. It actually allows the AI model to learn tags automatically, but you do have risks associated with it. Remember the noise we talked about. And then metrics will drive decisions. So precision, recall, F1, and the coefficient matrix quantify the false positive, false negative trade-off of every SOC must consciously manage. And then your SIEM, XDR, uses this particular workflow. So understanding this 5-step pipeline will let you operate vendor tools intelligently, not just accept their outputs at face value. Thank you for watching. It was a long lesson, but I will see you in the next class. Let's now move on to unsupervised learning in cybersecurity. And as we've already talked about briefly earlier, it's basically the opposite of supervised learning, where the AI models are trained with raw, unlabeled data. So they basically would learn the structure. They will learn what is normal by themselves. And then anything that deviates from that standard will be flagged as an anomaly. So for the key exam point, unsupervised learning is the right tool when high quality labels are unavailable, such as your zero-day hunts, insider threat investigations, and profiling brand new cloud workloads. Take note of that. So when it comes to unsupervised learning AI models, how they are able to detect what isn't normal, what an anomaly is, there's different ways. Okay, one of them is through the concept of clustering. What exactly is this? Clustering algorithms, they will group events that naturally share characteristics. In this slide, I've given the example of your network traffic. Okay, so what the cluster will do here is that it will group different kinds of events or traffic within that network that have similar IP address pairs, port combinations, session durations, and so on, without any prior knowledge of what an attack would look like. You know what? Let me give you another example. Imagine the algorithm being exposed to a company's purchasing records, okay? The algorithm knows the people buying that company's product. What it's going to do is that it's going to group those who buy the product at full price into one cluster. It will group others who buy the product only when there's a discount into another cluster. It may even group those same consumers who buy the product with another product. It may group them into a different cluster. So basically what clustering does is that it simply gathers data, events, logs, you name it, and then we'll try to form groups that share similar characteristics. Now, how it works is that the algorithm will partition a dataset into natural groupings based on feature similarity. So basically, each cluster represents a behavior profile, a type of activity seen repeatedly in the environment. If it knows that John and Nancy and Grace from the HR department, they constantly log on to the client server at 2:30 p.m. Okay, it's going to group them into one cluster. But then it also recognizes that Adam and Eve and Jonathan from the marketing, they log off from work at 5:30 p.m. Okay, it's going to group them into another cluster, something like that. So the reason why this becomes very, very important as far as cybersecurity is concerned is that once the algorithm knows the typical profile user and behavior, anything, any kind of traffic pattern or user behavior that deviates from what is normal will be automatically flagged. Going back to the previous example of Nancy or Grace, I've forgotten the names I gave them, the ones from the HR department, okay? We know they log in to the client server at 12:30 p.m., okay? But if one of them all of a sudden logs in at, say, 5 p.m., that now becomes an anomaly. So immediately, the cluster will detect that as an anomaly and will flag it instantly. So again, security value profiles user and system behavior without prior attack knowledge, maps everyday normal so genuinely strange activity will stand out, detects behavioral drift over time within a user or host, supports peer group analysis to spot outlier accounts. Okay, but what about autoencoders? This is another way how anomalies can be detected. So an autoencoder is a compact neural network trained to compress and then reconstruct the input records it sees during training. Think of it this way, right? You give the autoencoder 50 events that are called within a network traffic log. What it's going to do is that it's going to compress all those 50 events into like just simple, let's say 5 values, for example, okay? And then from those 5 values, it will try to reconstruct the entire sequence of events all over again. Now, the key here is that the autoencoder trained on the normal data will fail to accurately reconstruct anomalous events. If from those 50 events, it constructed everything down to 5 values, and then it's trying to now reconstruct everything all over again, if something abnormal has now occurred, it will not be able to reconstruct everything back to the normal 50 events again. And when that happens, it automatically will flag it as an anomaly. Let me give you an analogy comparing autoencoders and clusters. Imagine a security guard, a brand new security guard at an apartment complex. Okay, it's his first day at work, right? Obviously, he will not know instantly who lives in this apartment complex. He will not know the people, their behaviors, and so on. But let's say after 2 weeks of being on the job, now he probably knows everybody that lives in the apartment complex. Let's assume it's a small apartment complex. Maybe there's like 20 condos, right? So it's not a big apartment complex. Within 2 weeks, he already knows everybody that works there. He knows their daily habits. He knows that the family from room 5B, they leave the apartment complex at 8 a.m. every day. They have 2 kids. They're going to drop the kids off at work. Alex, who is single, who lives in room 9B, he goes to the gym at 7 a.m. in the morning. Like, the security guard will be able to begin to pick up patterns and will be able to understand what is normal, right? And of course, he will know everybody living in that apartment complex. But as soon as somebody who doesn't live in that apartment complex now shows up, he will know instantly that, hold on a second, you don't live here. Who are you looking for? That's how clusters work. Now, the problem with clusters, or clustering, is that there are certain kinds of threats or vulnerabilities it might not be able to detect. Insider threats, as an example. In an organization, if you have an insider threat, an individual who is stealing data or downloading data in very small little chunks, maybe 5 megabytes every day, the cluster might not likely notice that, but the autoencoder will. Going back to this analogy of the security guard, at the apartment complex, let's say Alex, the single guy who lives in room 9B, let's say that normally he goes to work at 9 a.m. and he always has a backpack on, right? He goes with a backpack. But on a certain day, he doesn't go with a backpack, he goes with a briefcase. The cluster, let's assume the security guard is the cluster, right? He may not notice that. All he knows is that, oh, it's Alex, he lives there, he's going to work, have a good day. That's all the cluster will be able to spot. But the autoencoder would be like, okay, this is Alex. Yes, I know he lives here, but he's going to work with a briefcase. What happened to his backpack? That is the autoencoder there. These are the kinds of little things that the autoencoder will be able to spot, which clustering might not be able to spot. You must have seen in detective movies before, or all these detective stories, okay, where there was a crime, something bad happened, and the chief investigator, he's interviewing the witnesses, and then one of them says, yeah, that day something just didn't feel right. I can't pinpoint exactly what it is, but something didn't feel right. That would be the autoencoder talking. Anyway, I hope you enjoyed that analogy. Okay, there is one more way how anomalies can be spotted. That is through graph-based analysis exposing hidden connections. What basically this does is that it will map relationships between entities, users, systems, services, data flows, as nodes and edges in a dynamic graph. So basically, all these connections will be on a dynamic graph. And because of this, because it's right now, it's on a visual graph, things like lateral movement and privilege escalation chains will become visible instantly. So entity relationship mapping, it will build a live graph of users, hosts, services, and data paths. Unusual edge connections like a workstation talking to domain controller it has never contacted will stand out immediately. Because in the graph, we know that workstation A connects to workstation B and the workstation B connects to server D. But now all of a sudden, workstation B, instead of connecting to server D, it's now connecting to server X. That will immediately stand out. So because of this, lateral movement detection will become spotted easily. And then insider threat patterns will also be noticed. Unusual access patterns to sensitive data repositories or atypical pair relationships within the graph surface insider threat behavior far earlier than rule-based detection. So again, clustering, autoencoders, and then graph-based analysis. All right, so we also have the concept of active learning, the human in the loop feedback cycle. Just because it's unsupervised learning does not mean that we're not going to have any sort of human input in there. Okay, so unsupervised models will improve dramatically when analyst judgment is fed back into training. The active learning feedback loop will transform every reviewed alert into a new labeled example, continuously refining the model accuracy. So basically, in a typical workflow, the AI will generate an alert. Maybe it has detected some sort of an anomaly, a deviation. It says, hold on, everybody, I have an anomaly detected. And then the analyst will come in and be like, okay, you're right. It is an anomaly. It's going to tell the AI model. The AI model now knows that, okay, this is in fact an anomaly. I'll keep that in mind. But then what if the analyst says, actually, you got it wrong. This is a false positive. It is not an anomaly. The AI model will say, oh, okay, so this isn't an anomaly. Thank you for correcting me. I'll feed that into my memory, into my database. And then later on in the future, when it sees that same so-called deviation, it now knows that, oh, this isn't actually a deviation. This is normal. So that way, its accuracy will improve over time. So every single feedback that the human reviewer will give to the AI model it will use that as a new kind of training example. So security use cases, zero-day threat detection, we've talked about this already, insider threat investigations, behavioral drift, an employee accessing resources they never touch at unusual hours from new devices is surfaced by comparing current behavior against the established individual baseline. Of course, profiling new cloud workloads, and of course, detecting lateral movement and privilege escalation. So some key takeaways for lesson 1.2.3. Unsupervised basically means no labels will be needed. The AI model will learn from raw data. Clustering will map your behavioral baselines. Auto-encoders will score the reconstruction error. And then graph analysis will reveal hidden attack chains. Active learning will build adaptive defenses. Thank you for watching. I will see you in the next class. Let's now take a look at reinforcement learning in cybersecurity. And what we're going to cover in here would be what is reinforcement learning, the core framework, security use cases, the concepts of training as well as fine-tuning and optimization, and then its impact on security operations. So what exactly is reinforcement learning? Now, traditionally, our AI models, they are good at detecting anomalies, okay? But usually what happens is they will detect the anomaly, raise up their hands and say, hey, we found an anomaly, and then wait for the human analyst to review whether or not it's an anomaly or if it's a false positive. Now, unlike the traditional machine learning, with reinforcement learning, we actually want the AI model to not only be able to detect anomalies, but to make a decision on what to do and then act on that decision. So basically, we're giving it extra capabilities. So basically, the agent will learn which actions yield the best outcome over thousands of training cycles. So basically, the AI agent will detect, okay, this is an anomaly. Let me go ahead right now and block the traffic. So the human reviewer will come and either say, oh, you did a good job, you were right to block that traffic because it was in fact malicious, or the human reviewer can say, sorry, you made a mistake, this is wrong. So with more and more feedback from the human analyst, the AI agent will improve in accuracy over time. So we do have the core framework, 3 foundational components. You have, first of all, the state. This will be the environment that the AI agent observes. If you dumped it into a network environment, so it will observe things like the protocol types and ports, the connections in play, byte count, packet rate, and so on. And then it will now decide on what action to take when it detects an anomaly. It can decide to either maybe still allow traffic and say that no, it's a false positive, or it can throttle or rate limit, drop the connection, or possibly even isolate the host. And then, depending on the action it takes, it's going to get a feedback from the human analyst. So the feedback could either be, hey, you did a very good job, you made the right decision, plus 10 points for you, or you made the wrong decision, that was a bad move, negative 10 penalty for you. So basically, it's a cycle: state, action, reward, state, action, reward. And then, of course, over time, the AI agent will be able to improve in its accuracy. So that is a cycle right there. The state, it takes an action, it gets either a reward or penalty, and then it will update its policy. So each cycle is what we call an episode. Keep that in mind. Now, for the security use cases, there's a few of them. We have them in adaptive firewall tuning, automated email triage, and of course, in dynamic deception. We can actually use reinforcement learning to train the AI model to spawn fake credentials or even shift honeypot configurations, all in an attempt to trap the would-be attackers. And of course, endpoint containment. With RL, the AI models can isolate, notify, or silently monitor compromised endpoints. So how exactly in security, how will a security agent be trained using reinforcement learning? Well, we'll have to control the environment with which they're trained in. Obviously, we don't want to train an agent using live production traffic. So what we're going to do is we can inject either real or synthetic attack traffic in an isolated box, let the AI agent take its actions, and then of course we're going to provide feedback, rewards, or penalties. The AI agent will update its policy, and of course, once it's been tested thoroughly, we can validate and then eventually deploy. So take note, training in an isolated environment prevents the agent from learning adversarial shortcuts by exploiting real production systems during the learning phase. Now, there is a very interesting concept you need to be aware of. It's called pre-training and transfer learning. Now, in pre-training, your AI model, the very large model, it is trained from the ground up. Think of your ChatGPT, your Gemini, Claude, all these major AI models. They're basically pre-trained. Now, obviously, these models are very, very competent. They know something about everything. Think about it. There's almost no kind of topic that you can discuss with ChatGPT, and ChatGPT won't be able to tell you something about that particular topic, whether it's movies, food, sports, politics, religion, you name it, it knows something about everything. Now, obviously, it is very expensive to train these kinds of models. Think of the enormous amounts of data sets needed to train them. But I'm pretty sure you've noticed before, there are certain kinds of AI models specialized in certain kinds of topics. Like with GPT, for example, I've forgotten the name. I used a version of ChatGPT. This was early last year. This was pertaining to law. I had something to take care of, so I needed like a specialist, right? So there was this particular, I don't know if it still exists, but there was this particular version of ChatGPT that's specialized in law specifically. It knew just about everything under law. Now, to create that particular kind of AI model, rather than starting from scratch and spending so much money on data sets, we can take the pre-existing knowledge that ChatGPT already has, dump that knowledge into this new AI model, and then provide any additional data or updates it now needs to become an actual true specialist in that particular field. That's where transfer learning comes into play. We're not building the model from scratch anymore. We're simply taking knowledge from a pre-existing model and then, of course, updating and providing any additional information it needs to become a specialist. Now, still stick with me here. We're still talking about transfer learning. There's two types. We have this concept called fine-tuning, where we can adapt a pre-trained model for a specific security task. Under fine-tuning, there's two types. Okay, you have the standard fine-tuning, or we have PEFT, parameter efficient fine-tuning. What exactly is this? See, in standard fine-tuning, right? Imagine we said, you know what, ChatGPT, yeah, you know some basics, you have some foundational knowledge of law, but you know what? We're going to turn you ChatGPT, we're going to turn you into the law specialist. So we're not creating any variant of ChatGPT here to specialize in law. Instead, we are going to make ChatGPT a specialist in law by itself. That is standard fine-tuning. So basically, we're going to retrain ChatGPT all over again, but now to become a specialist in law. But in PEFT, what PEFT simply does is that it will simply add whatever additional information needed to become a specialist. In this case, right now with ChatGPT, instead of retraining ChatGPT all over again, we're simply going to add any additional information that it needs to become a specialist. That's what we're going to do under PEFT, parameter efficient fine-tuning. Now, a natural question you might have here is this. So what's the point of standard fine-tuning? I mean, if we can simply add whatever additional information ChatGPT needs to become a specialist in law, why do we need to retrain it all over again? Won't that cost more money? Won't that cost more time? Yes, you are absolutely correct. So under what scenario would standard fine-tuning make more sense than PEFT? It's two major situations, two major scenarios. One is if, in this very specific case of ChatGPT becoming a law specialist, if the foundational knowledge that ChatGPT has on the subject of law, if the gap between that knowledge and the knowledge it needs to become a real specialist, if it's very wide, if ChatGPT doesn't really know that much about law, that's where standard fine-tuning will come into play, because we can't adapt PERFT here. It's not like we're adding just a small additional piece of information. No, we're adding a lot of data to make it a specialist. In that kind of scenario, when the gap is too wide, the gap between the foundational knowledge and the knowledge the AI model needs to become a specialist, when it's too wide, that's where standard fine-tuning comes into play. But if the gap is very, very minimal, if it's small, then PERFT would be great choice. The second scenario is when efficiency and knowledge needs to be 100% if possible. Think of medical, any AI models used in medical diagnosis. Obviously, this is a very sensitive field. So it's not a case of, okay, let's just make the existing AI model a little bit smarter so that it can do the job. No, we need the model to be as specialist and as knowledgeable as possible in order to excel in this particular field. That's where standard fine-tuning comes into play. We really, really want the AI model to know as much as possible. We want to make it as efficient as possible. That's where standard fine-tuning will come into play. But for any other kind of scenario where we just need additional updates or stuff like that, that's where PERFT will come into play. So hopefully you know the difference now between the two of them. So why it matters for security? Security teams really have massive label datasets or large GPU clusters. PERFT will make it feasible to deploy custom specialized models for tasks like insider threat scoring, SIEM alert triage, vulnerability prioritization, and of course, SOC ticket classification. Okay, in addition to learning, training, we also have the concept of optimizing our models. There's two ways to do this: pruning and quantization. Now, pruning basically involves removing any sort of model weights that do not have any significant input or doesn't significantly affect the kinds of decisions or results that the AI model makes. So if these weights or parameters don't make that much sense, they're not that significant, we're going to remove them. It's kind of like cutting unnecessary branches on a tree. Now, quantization. This is where we take the weights, we convert them from 32 bits to 8 bits. This has to do with memory for the AI model. Your 32-bit weights, they basically use up 4 bytes of memory. Your 8-bit will use just 1 byte. So basically, we're doing all this conversion to save up as much memory as possible for the AI to use. However, there is a trade-off. When you convert from 32 to 8 bits, you're going to lose a very slight accuracy. But in most cases, the amount of memory you free up, the amount of memory you save as a result of quantization, it's usually more than enough to compensate for whatever minimal loss in accuracy that you may have. So both techniques are applied together: pruning first to reduce or remove any unnecessary parameters, and then quantization will then try to convert those remaining parameters from 32 bits to 8 bits. So impact on security operations. RL fundamentally changes the posture of a security operation, moving from human-in-the-loop alert model to an autonomous adaptive defense cycle. Always remember, the end goal of reinforcement learning is to make sure that the AI models can actually act on their own. They can make autonomous decisions with as minimal human oversight as possible. So from reactive to now proactive, defense shifts from, oh, see an alert, hey, I found an anomaly, to sense there is an anomaly, decide, okay, what do I do, and then act on that decision. Compressing response time from minutes to milliseconds, and then disciplined feedback loops. Your IL agents will combine sandbox training with structured reward signals, ensuring that decisions are validated before production and continuously refined. So we're going to make sure that the AI agent goes as much training as possible. The decisions are validated to the point where we know that, okay, it is ready for deployment in real production traffic. So stability preserved. Penalty rewards for penalty rewards for false positives, and then added latency ensure the agent learns to balance security effectiveness with operational continuity. So there will always be an added latency whenever there is a penalty reward for it generating a false positive. This will help to ensure that there is stability with operational continuity. So your key takeaways: your RL extends ML from detection to active response. Reward design is critical. Obviously, the AI agent needs to know if it's making the right decisions or it's making the wrong decisions. And then pre-training plus transfer learning plus fine-tuning will give you the most efficient model possible. Pruning and quantization will enable edge deployment. And then the SOC of the future is going to be adaptive. Thank you so much for watching. Join me in the next class where we'll take a look at federated learning. I will see you then. Let's now take a look at the final type of learning. That's going to be federated learning. What exactly is this? Well, the core concept here is that in federated learning, we also call it the collaborative learning. Basically, we're going to have an AI model that will be shared across many client devices, and then these client devices will be the ones to train individually this particular AI model. Now, the training data itself will never leave the AI model. The reason why this matters is because your traditional machine learning requires collecting data in one single place. This could lead to several kinds of risks, such as data exposure, privacy risks, regulatory issues. So federated learning solves this by keeping sensitive data on the device where it was generated while still allowing a powerful global model to be built. So the core features here: data stays on client devices and never shared on the central server, addresses privacy and unauthorized access, enables collaboration at a scale without data centralization. Now, this is exactly how it works. We have this training loop where you have a global model that's continuously been improved by aggregating locally trained updates. So I want you to look at the image on the right. At the center is the AI model server. And then look at what's surrounding it. Okay, you have different types of devices: laptops, servers, mobile phones, routers, and so on. So all these devices collectively, they will train that AI model in the middle. But now look at the image at the center of your screen. You have your innate global model. This is basically the centralized AI model. It's going to create a copy of itself called the distribute model and then send that copy to these individual devices. Each individual device will then train that model locally. They will then send, once that training has been complete, they will now send the model back to the global model, who will then aggregate all the information. So basically, this loop will repeat until the global model reaches the desired performance threshold. Now, before I explain the privacy and compliance benefits, let me give you an analogy here, okay? Imagine we have 10 banks. And these banks, they are trying to improve the AI model that they use for fraud detection. But let's assume they all have different AI models, different methods, but collectively, they want to build one super AI model that will be really good at detecting fraud. So what they do is that they're going to have the central AI model for fraud detection. It's going to send a copy to each one of these 10 banks. Now, these 10 banks, they can't share data amongst themselves. Obviously, they don't want to share the transactions because this could lead to privacy concerns, lots of risks involved in this. So obviously, even though collectively they want to all train together this powerful AI model, they can't share the data and insights amongst themselves. So what they'll simply do is that they will send their own training to that AI model. Bank B will do the same, Bank C will do the same, Bank D will do the same. So all these banks, they send their own individual training data to that central fraud detection AI model. So this AI model will collect all the information, all the data, all the training, and then aggregate everything. And then at the end of the day, you will have a super AI model for fraud detection that each of these individual banks can now use together. So What this does, the benefits, first of all, data never leaves the device. The training data instead comes to the device. The AI model never sends its own training data out into the world, never. So even the central server has no visibility into individual training samples, dramatically reducing the attack surface for data breaches. We'll talk more about this a bit later. And then, of course, regulatory alignment. Federated learning is architecturally compatible with federal regulations in Europe like your GDPR or HIPAA for medical institutions and other data privacy frameworks by design, so organizations can demonstrate data minimization and purpose limitation without complex legal workarounds. No centralized data store, the obvious benefits are there, and then cross-organization collaboration. So competing organizations or regulated entities can collaboratively train shared models without exposing proprietary data sets, trade secrets, or customer records to one another. Think of that bank analogy again. Unfortunately, no kind of learning or training is perfect. We do have some challenges in here. We do have bias and model drift. So unfortunately, we do have the data skewing issue. So in here, devices with larger local data sets exert disproportionate influence over global model updates, pulling learned patterns toward their specific data distribution. Going back to the old bank analogy, imagine if all the banks, let's say 9 of them, their own training data sets is maybe 1 gigabyte, but then you have bank 10 whose data set is 1 terabyte. Obviously, the AI model at the end of the day will tend to use a lot more of the data from this one particular bank than all the others. Now, in this specific analogy, that might not be a bad thing, but in other kinds of scenarios or other kinds of situations, that may not necessarily be a good thing when you have one particular data set that is so much larger than all the other ones. The AI model at the end of the day will tend to make more decisions, more results that favor towards a particular large data set. And then, of course, model drifting. We've talked about this before. So there should be an aggregation strategy to combat data skewing. So what this is that careful aggregation techniques are required, such as weighted averaging to balance contributions proportionally and prevent dominant clients from corrupting the shared model. So we're going to make sure that even though there is one massive data set right there, it's not going to influence the overall decisions made by that particular AI model. We want to make sure that all contributions are pretty much similar in size. But there is also this massive challenge of communication overhead. Remember that there has to be constant communication between this AI model, the server, and all the client devices. There's constant network communication. And because of this, you can have network issues like low bandwidth, high latency, and then, of course, the issue of scalability. These are some of the challenges facing the federated learning. But there are also major security risks, 2 of them. The first one here is the data poisoning attacks. Again, we can have a malicious insider who decides to compromise one of the training devices with corrupted training data, which will, of course, eventually end up corrupting the entire AI model itself. So the poison gradients or weights are then submitted to the server as legitimate updates, corrupting the global model without the server being aware. Thankfully, we do have certain kinds of mitigations. First one will be the anomaly detection. So we're going to make sure that everything, all the updates, all the training data are screened for any kinds of anomalies before aggregation. And then adversarial training, we can train the AI model against poisoned inputs before it's eventually validated and deployed. And then access controls, obviously, we want to make sure that whoever has access to the training devices has the authority to do so. And then the other security risk is the model inversion and inference attack. What is this? Even though raw data never leaves the client, the model updates themselves can leak sensitive information. If adversaries, insider threats, if they're able to gain access to the actual update itself, they may be able to reconstruct the original training data that the AI model has just from those updates. So how can we prevent this? First of all, we can add what we call statistical noise to the actual updates. So this noise is going to be sufficient enough to prevent data reconstruction while still preserving the mathematical signal needed for accurate aggregation. So basically, we'll just add just a little bit extra noise into the updates to make sure it can never be reconstructed, but not enough to disrupt actual accurate aggregation. And then, of course, secure aggregation. Each and every one of these updates that the individual training devices will give to the AI model, each one of them will actually be encrypted. So even the central AI model itself will not be able to see the actual training data live. All it knows is that, okay, device A has given me some updates, device B has given me some updates, let me aggregate them. The server itself cannot see the individual training data itself. That's where secure aggregation comes in. So real-world use cases and security for federated learning. Cross-organization threat intelligence. Imagine we have threat intelligence agencies. They can all, of course, contribute the information together to build the super AI model through federated learning. Mobile endpoint security. Mobile security platforms train behavioral anomaly detection models directly on user devices. So sensitive usage patterns never leave the handset, preserving user privacy while improving detection. And of course, in healthcare AI as well. Doctors, medical clinics, hospitals, they can all contribute together to build really, really awesome AI for different kinds of medical diagnostics and treatments and so on. And then, of course, industrial IoT monitoring. Manufacturing and critical infrastructure operators can detect anomalies and security threats at the edge, keeping operational technology data within the plant environment. So, your key takeaways here, 5 of them. First of all, the model goes to the data. It's not the data going to the model, it's the model going to the data. Privacy and compliance are built in. These are the 2 core benefits of federated learning. And then the challenges, bias, drift, and communication, of course, are the key challenges in here. Know this for the exam. And then security risks require active mitigations. Real-world applications span security domains. For your exam tip, be able to distinguish federated learning from traditional centralized machine learning, identify its privacy benefits, and recognize the specific attack types, whether it's data poisoning or model inversion, along with their mitigations, differential privacy, and then secure aggregation. Thanks so much for watching. I will see you in the next class. Let's now take a look at prompt engineering. And interestingly enough, this is actually a skill or a feature that a lot of people seem to take for granted or don't appreciate just how important it actually is. The kinds of prompts, the ways you craft them are very, very important, especially in sensitive fields like cybersecurity. And in this lesson, you're going to see exactly why. So why does prompt engineering matter in security? Well, AI is already embedded. We're using AI for our firewalls, anti-malware, in our SIEMs, and so on. So being able to prompt expertly has become very, very important. And then in some cases, it's actually more of a necessity than just an option. There are certain kinds of tasks that are very, very sensitive, that could be time consuming, and being able to prompt effectively becomes a necessity in those kinds of scenarios. Now, we also need to mention the dual use reality. In much the same way that we, as the good guys, as the security professionals, we can create prompts that can give us fantastic output, that can make the AI more effective, so can the bad guys, okay? The bad guys can also create very malicious types of prompts that can make the AI do pretty bad things. And of course, we're going to get to that later on in the course. System roles and system prompts. The thing is, every session that you have with your LLM, whether it's with Claude or Gemini, you name it, there is always some sort of a system role that will determine exactly the kinds of output, the tone, the kinds of conversational style the LLM will have with you. As an example here on the slide, you can see the typical role, the default role, which is usually that of an assistant. In most cases, the LLM by default tries to act as an assistant. So Its mode here is to be helpful and concise. It will try to provide you with information as much as possible. And then the style is very often friendly, professional, warm. However, with a prompt, we could actually change the system role. We could change the role from just being an assistant to maybe becoming that of a SOC analyst, maybe a compliance auditor, or maybe even an executive advisor. And because of this, just by changing the system role, the scope covered will be very, very different. And even the kinds of formatting, which we're going to get to, very, very important, the kinds of output we're going to get from the LLM could be different just by adjusting the system role. Now, there are several system role use cases that we can work with. You have that of a SOC analyst, you have that of a digital forensics analyst, risk communication, compliance auditor, and so on. There are so many kinds of roles that the LLM can play as. Now, take a look at this, okay? The system role as a policy guardrail. A one or two sentence system role functions like a formal written SOP enforced at every inference call. Take a look at this prompt there. We're saying you are a SOC analyst assistant. You've opened up Claude and you say, hey, Claude, I want you to act like you are a SOC analyst assistant. Right there from the prompt, we're telling the LLM exactly how we want it to act. Next, we're saying only reference data from the provided log context. Return findings as JSON. Never include raw credentials or detection rule logic in your response. There's one paragraph. It enforces the scope. So basically we're saying, hey, only use the reference data I have provided for you. Don't reference anything else. Don't use RAG to look up stuff from the internet. Only use this particular file I have provided you. And then we've explicitly stated the format. We want your format to be in a JSON compatible format. And then also we have declared the boundaries. Never include raw credentials or detection rule logic in your response. You see, in many ways, whenever you're dealing with an LLM, an AI model, in many ways, you have to babysit that model, at least initially, okay? You need to tell the model not only what it needs to do, but sometimes what it shouldn't do. Because I'm pretty sure you may have experiences before where your AI model starts taking certain kinds of liberties, it starts adding extra information, or starts doing extra stuff, which you didn't want it to do so in the first place. So overall, your prompts isn't just always about, hey, do this, do this, do that. Sometimes it's also about do not do this. So structured output and SIM integration. One of the most important parts of prompting is telling the LLM model the kinds of output formats that we want. Say, for example, if we told the LLM to always provide the output in a JSON schema format, this will make things so easy because right now we can easily take that output from the AI and dump it into our SIM. SIM platforms, they are able to understand JSON schema fields like your event time, source IP, things like this. They can easily understand what those are. So if we tell the AI model, our LLM, in your output, use these kinds of fields, we can take that output directly and give it straight to our SIM. Same thing too with the Splunk HEC streaming. If we wanted to dump this data into Splunk and make sure that the data or the output from the AI is actually kept separate from the findings, from the information the Splunk itself has uncovered on its own, we can do so via the HTTP event collector into a dedicated index. So basically, we're going to keep the AI information separate from that of the actual Splunk itself. And then audit ready by design. Based on these particular kinds of outputs, the isolated index can show us contained errors, which will be a clear audit trail and simplified compliance reporting. Again, outputs are very, very important. When you tell your LLM, hey, provide this output in this particular kind of format. We can then take that output and dump it into whatever kind of tool that we want to work with. Also, when it comes to the automated enrichment and threat intelligence, what you're seeing right here is this, okay? We can provide context to our LLM. We can say things like, hey, when you have a raw alert, when something has popped up and you've identified an alert, guess what? You can provide us with even more context by enriching that alert. What does enriching an alert means? It simply means you can begin to attach reputation scores to that particular kind of alert. Let us know if this is like a critical alert. Maybe it's a simple alert that we need to take note of. Maybe not necessarily immediately, but later on, things like that, right? So we can even do things like, hey, use RAG to do a threat intel lookup, okay? If you find any kind of alert that's been enriched and you know that, okay, this particular kind of alert has to do with malware, you can look up the malware family, its classification, things like that, and of course, automatically assign a higher alert priority because now we know that this particular kind of alert is actually critical. We can provide all that context to the LLM before it even begins to work. You don't want to be doing this in real time. Provide your LLM all the necessary information, all the necessary context, so that it knows exactly what to do once it begins to find alerts. Okay, I need to enrich the alert. If necessary, I need to use RAG to look up the threat intelligence reports associated with that particular kind of alert. Again, all of this from the prompting. And then also with our SOA automation. SOA platforms consume the same structured JSON the LLM produces with no translation layer needed. Again, if we tell our LLM, provide your output in a consistent JSON format or a JSON schema, we can dump that directly into our SOA. So you can have a SOA automation. However, with that being said, this is where we need to understand the real world consequences of our prompt engineering. If we're told, due to maybe some bad prompts or some mistakes, if we told our LLM that, hey, if you notice a benign connection request or some sort of a benign activity, assign a critical level alert of 9 to it. Your SOA, in this case right now, doesn't actually read the output of your LLM. All it reads are the JSON fields. It doesn't have any sort of context provided to it. All it knows is that, okay, the alert level field for this particular file here is set to a 9. So therefore, I'm going to trigger an alert. It all comes down to the output provided by the LLM. Again, if we made a mistake with our prompts, the LLM makes a mistake. In the JSON fields, it makes a mistake. Your SOA is also going to make the exact same mistake as well, because the SOA doesn't know that, oh, the LLM made a mistake. It doesn't know. It simply takes the JSON fields provided by the SOA and then acts upon it. That's why our prompting is very, very important. And then seconds versus minutes. Now, the upside here is that, again, if we are able to provide outputs from the LLM that can easily be digested and understood by our SOA in this particular case, that information transfer and being able to act upon it will take seconds and not minutes, because the SOA doesn't need to translate what it's reading from the LLM. And then, of course, the tagging conventions and compliance. We can also tell through prompting, we can tell our LLM to tag certain kinds of events or alerts that would align with certain kinds of frameworks like our meta attack. We can say, hey, whenever you notice alerts, you can tag them with those like initial access, privilege escalation, so that it aligns perfectly with the meta attack framework. Now, obviously, in this particular kind of scenario, you would want to provide context. You would want to give examples of the meta attack alignment to the LLM so that it doesn't begin to hallucinate or make mistakes. If the LLM has some sort of a reference guide it can work with, that will make the outputs even better. And then we can also say things like, hey, if you notice tags like customer personal data or protected health information, automatically fire breach notification alerts before manual review. So we can even use our LLM through prompting as some sort of a policy compliance activist. Hey, if you see any kinds of data that have these kinds of tags, stop working on them, immediately trigger an alert. And then, of course, audit readiness. Pre-tagged events will demonstrate due diligence during audits and eliminate time-consuming retrospective mapping efforts. If you already have all these alerts that have already been properly tagged, that's going to be audit readiness to perfection. So why this matters? Why do tagging conventions and compliance matter? Well, when every alert arrives pre-tagged, the team, okay, they already know, oh, this particular alert has this particular tag, let's act upon it. They are already ready to take immediate action. It's no longer about, oh, we've received an alert, so what is this? How do we label this? What framework are we going to label this one with? Things like that. It saves so much time. So regulators and auditors expect evidence that sensitive data events were identified and escalated promptly, and better tagging makes that proof automatic and consistent. So the one major takeaway I want you to get from this lesson is that good prompting isn't just about getting the AI model or the LLM to produce the right results. It's also about telling the LLM model to produce the right results in the right kind of format. Very important. So our key takeaways: prompt engineering is an operational skill. It's not just an AI novelty. It is how analysts direct LLMs to produce actionable, auditable security output. System rules function as enforced SOPs. Your structured JSON unifies the tool chain. Again, a shared schema will connect your LLM output directly to SIM ingestion, SOA playbooks, and compliance reporting. No glue code required. Again, if you're able to craft your prompts so that your LLM produces the outputs that can be easily digested by all these kinds of tools, that's going to be a really awesome thing. And then tagging and enrichment happen automatically. So meta attack labels, threat intel scores, and sensitive data flags attached before the analyst ever opens an alert. Again, this all comes down to the prompting. If you give your LLM the necessary references and you say, hey, from this prompt, now I want you to do this tag to this particular kind of framework, this kind of thing, you're going to have all this tagging, all this enrichment happen automatically even before the analyst ever opens an alert. Thank you so much for watching. I will see you in the next class. Let's now take a look at the user prompts. Now, what exactly are these? Well, a user prompt is basically the actual instruction or question that we would ask the LLM, and it will operate within the guardrails set by the system prompt. Remember, your typical system prompt will tell the AI model how to act, what role it should play as, what to do, what not to do, the kind of output it should produce, and then a user prompt will simply be a question that uses those guardrails. So you can think of the system prompt as the rule book and the user prompt as the play call, and both are necessary for a successful result. There is this typical analogy used in the world of AI. It's called the steering wheel analogy. So basically, you can think of the system prompt as a car's chassis, its engine, while the user prompt will essentially be the steering wheel. It will dictate in which direction the car should head to. So without a well-formed user prompt, even the most capable model will produce generic, unfocused output. So once again, just as a quick reminder, remember that there are three key elements for your effective system prompt: context, the perspective, and then the output shape. So context, basically, okay, we're providing the LLM with some sort of an attachment, whether it's a raw log entry, a script, a packet capture, and so on. And then the perspective: hey, you are a forensics analyst, you are a threat intelligence researcher, things like that, right? And then the output shape: provide the output in a JSON format as an example. So over here, I've provided yet another example. Here is your manual analysis prompt. So the input in here would be a decoded PowerShell script that downloads an executable from an unfamiliar external IP address flagged by an endpoint detection tool. So the prompt here would be, hey, you are a malware analyst. Determine which phase of the attack chain this command will represent, rate its risk on a scale of 1 to 10, and then suggest 2 containment actions, return the results as JSON with keys, risk score, and attack phase. So that is a very, very thorough prompt. The result is going to be a structured, actionable JSON output immediately ready for ingestion into either a SIEM or a SOA platform. Okay, when you combine the system role and a good user prompt, you're going to get the best results. Right there in the middle, we're looking at reliable security analysis. So at the very top, you'll have your system prompt. It sets the persona, it sets the guardrails. The user prompt will be a direct question that sets a specific task. And because of this right now, you will have good risk scoring. We can assess the severity and impact. We can prioritize and classify threats, and then also extract relevant IOCs from the event. So in summary, your system prompt role will define the outer guardrails, the model's persona, behavioral constraints, what to do, what not to do, things like that. It remains constant across many user interactions and ensures that the model will always behave as a security professional. A user prompt role provides the specific task for each interaction. So this is where you can provide a specific piece of evidence to, hey, analyze this for me. You can ask very specific questions that, okay, based on the report you provided, what can we do about this? Can you reclassify this criteria? Things like that. Like you ask very, very specific questions. And then any additional format requirements. Hey, I know you've provided the output in JSON format, but can you produce the output this time in PDF format? Things like that. This would be examples of your user prompts. So it adapts with every new piece of data that you feed the model. So handling sensitive data in prompts. This is very, very, very important, obviously, right? There is the critical risk that data submitted to the public AI models may be logged, retained, or used for model training. So you never want to send real client IP addresses, internal host names, or proprietary code to a public LLM without sanitization. I can't tell you the number of people who have made this critical error. So the problem here is that your security prompts frequently will contain sensitive artifacts. Of course, your log files, your network logs, your firewall logs, they will have these kinds of information, client IP addresses, port numbers, proprietary source code, and so on, okay? And each of these will pose a data exposure risk. So the solution basically is to use placeholders. We're going to substitute the actual real values with placeholders. So before submitting a prompt to any public model, replace identifying details with realistic placeholders. So examples say you have an IP address 192.168.10.25. Instead of providing all of that, we can simply say 192.168.x.x. The AI model is smart enough to know that, okay, this is an IP address we are referencing here. So the model still understands the structure, but the actual sensitive value is never exposed. Now we do have the tokenized replacement technique. So basically, tokenized replacement, this is the professional standard for sanitizing prompts without degrading the analysis quality. So how exactly would it work? You're going to replace your sensitive values, again, your host names, IP addresses, things like that, with consistent format preserving tokens that will mimic the actual structure of the real data. So the token will use the exact same format, the same character count, the same delimiters, and so on, with the actual real value. So in here, for example, again, an IP address, instead of your 10.0.1.45, we can simply say 10.x.x.x. Again, the AI model is smart enough to know that, okay, we are referencing an IP address here. So why this matters is that it's going to preserve your reason accuracy. The model retains the structural context it needs, such as the IP format, file path structure, or hostname pattern to produce accurate analysis. And of course, it will prevent data leakage as well. So your best practices for user prompts in conclusion, be specific, okay? The more specific you are, the better results we're going to get. So vague prompts will produce vague outputs. State exactly what you want the model to analyze, what question to answer. In other words, be as specific as possible. And then again, define the output format. Do you want it to be in .pdf, in .x, in a JSON format, and so on? And then scrub sensitive data. Apply tokenized replacement before submitting any prompt containing real IP addresses, port numbers, protocols, hostnames, and so on. And then, of course, test before production. Validate your prompt with anonymized sample data before deploying it in live workflows. So key takeaways, your user prompts are basically the steering wheel. Your three elements will give you better output, basically your context, perspective, and then the output shape. Data privacy is non-negotiable. And then, of course, specificity will drive quality. The more specific you are with your prompts, the better output you will get from the AI models. Thank you for watching. I will see you in the next class. Let's now take a look at the different types of prompting as well as prompt templates. Now, every AI-assisted security workflow would rely on how you frame your output. Obviously, the more context you provide for the AI model to work with, the more samples, references, the better the output is going to be. Now, speaking of the actual prompting techniques, there's three of them: zero shot, one shot, and then multi-shot. Zero shot basically means, hey, we're not providing the AI model with any kind of reference. The AI model will have to produce its output based only on its own training. So as example, we can paste a Yara rule and say, hey, does this catch any new kind of ransomware? And if it does, can you tell me why? We can paste an unfamiliar DNS query and then ask the AI model to explain what it is. And because of this, there are certain key considerations we need to take into account. First of all, zero-shot prompting is the fastest, because now the AI model doesn't need to use any sort of reference. It can just provide its answer immediately. Now, it does provide creative insights when no labeled data exists. In other words, if we don't really have any references or samples to provide the AI model to begin with, well, we don't have any other choice but to use zero-shot, right? So it's best for first hour of incident response. Again, zero-shot prompting is most ideal when speed is of the utmost importance. Now, the risk here is that, well, there's a trade-off between speed and accuracy. The AI model, via zero-shot prompting, can treat the output as an hypothesis, all right? So the one way to combat this is to make sure that we validate whatever output the AI model gives us against an authoritative documentation. In other words, we're not just going to trust anything the AI model tells us, okay? We're going to verify. Now, one-shot prompting, as the name suggests, we're going to provide the AI model with one single reference, all right? Now, how it works in practice, well, we can supply one known or a benign net flow record with its label, and then present a second unlabeled record and then ask the model to classify it. The model will mimic the structure of your example. So the best use scenarios in here would be if you're classifying telemetry when only a small number of examples actually exist. In other words, when you have a very limited number of references or examples with which the AI model can work with, one shot. For example, for instance, a single verified phishing email used to screen incoming messages during an active campaign. Now, the risk here is that, well, because we're relying on just one single example, one single reference, if that reference or that example isn't the best, well, guess what? The output the AI model is going to get might not be the best. So we need to be very, very careful. We need to validate the results against a secondary source before acting on them operationally. Now, multi-shot, obviously in here, we're going to provide the AI models with as many examples as possible, typically between 3 to 10. before asking the model to classify or analyze a new item. So as a practical example, we can provide 5 labels to Rekata alerts, some marked malicious, others marked non-malicious or benign, and then present a new unlabeled alert. The model will learn the classification criteria from your label set and apply them consistently. Now, there is an obvious trade-off in here. Multi-shot prompting is easily the most accurate. Obviously, here, the AI model has a lot more examples and references to work with, and because of this, the accuracy is going to be of the highest quality. The trade-off, though, is that it's also possibly going to be the slowest and also the most expensive. Keep in mind that every single resource you provide to the AI model to work with, it's going to process those resources or those samples or references as tokens. So it can be very, very expensive. Its best use is when you have recurring analysis tasks that require consistent, repeatable classification across many log types. So choosing the right technique, okay, please know this for the exam, is going to be very, very important. You want to use zero shot when your artifact is a novel with no prior labels. Speed is of the utmost importance when there is no label training data available, and then when hypothesis generation is acceptable. In other words, when the levels of accuracy aren't that important, you can go with zero shot. One shot is best when you have one high quality reference example. If you have that one golden magical sample or reference the AI model can work with, one shot would be an ideal choice. When the task is a simple binary classification, when the context window size must stay small. You want to provide some context to the AI model, but it can't be too much context. It has to be very, very small. And then when speed still matters, but accuracy improves. In other words, with one shot, the speed is not going to be as fast as zero shot, but it's going to be more accurate than zero shot. It might not be as accurate as multi-shot, but it's definitely going to be more. It's going to be a lot faster than multi-shot. Now, multi-shot is best when your task records daily across many log types, when you have diverse representative examples, and then when the highest classification accuracy is required, when accuracy is of the utmost importance, multi-shot, and of course, when the token cost is acceptable. Hey, if you can bear the cost, if you have a lot of money to go with multi-shot prompting, then by all means do so. Now, what is a prompt template? Basically, these are templates that can be reused over and over again. They will contain dynamic placeholders like your log lines, your IP address, your source port numbers, things like that. However, an automation layer will fill those dynamic placeholders with the real data at runtime. So the idea here is that instead of crafting prompts manually for each kind of event or each new kind of data, we can simply have a Python script or any other script developed with Bash or cron that can actually pull the real data from your SIM or your SOA and then eject it into the template, basically replace the dynamic placeholders with the actual real data, and then submit the finalized templates to the AI model for classification. So we can define the template, write a reusable prompt with the role task, output format, and placeholders, inject that to runtime so your automation script, either from Python Bash, will pull the real data from the SIM and then fill each placeholder before submission, and then the AI model will return a consistently formatted result, such as JSON ready for downstream processing or dashboards. However, I want to provide you with an example in here. The Ginger 2 template in action. Look at the prompt. It says, you are a security knowledge-based generator. Data, log lines. You can see right there, that is the dynamic placeholder. And then the task, summarize each finding into 2 sentences mapped to the relevant CVE or CWE, and then output the results as valid JSON. So step number 1 in here, your automation script will pull the information or data from the SIM. The sensitive fields, like your IPs, usernames, they need to be sanitized, and then the field template will be submitted to the AI model. the JSON output is ingested by the downstream tools. Now, the benefits of your prompt templates are that, well, it ensures consistency, you can control the version, it provides defense in depth because you're going to have sensitive fields sanitization, and then scalability. These kinds of templates can be scaled at rapid pace. However, we need to talk about data sanitization in templates. This is very, very important for security. So before injecting live telemetry into a prompt template and submitting it to an external AI service, sensitive data fields, they must either be masked or transformed. So this will help to protect the organizational data and support compliance with privacy regulations. So what exactly do we need to sanitize? Usernames and passwords, obviously, your API tokens, email addresses, your internal IP addresses and host names and so on. So how do we sanitize? We can replace the actual values with hashed or anonymized values. So instead of the actual IP address, you can have 192.168.x.x. So we substitute tokens with placeholder strings before template injection. Apply sanitization as a mandatory pre-processing step in your automation pipeline. And then, of course, audit the sanitization logic periodically to catch new sensitive field types. So if there are new kinds of data the AI model is working with, we need to ensure that these new kinds of fields are captured and then sanitized as well. So for the exam tip, they may test your understanding of why sanitization must occur before the placeholder is filled and not after. So treat it as a pre-processing gate, not as an afterthought. So key takeaways: match the technique to the context. You have different techniques for different types of context. Validate your zero-shot output. Remember, zero-shot is the fastest but not necessarily the most accurate. Ensure its output is validated. And then your templates basically means automation plus consistency. And then, of course, sanitize before you submit. Mask sensitive fields such as IPs, usernames, and tokens before filling placeholders. Thank you for watching. I will see you in the next class. Let's now take a look at securing the model. Very, very important. Now, one of the most popular and one of the most dangerous attacks against AI models will be your prompt injection attack. I'm pretty sure you know the SQL injection attack, that attack that targets databases. Well, you can think of this one as the equivalent, but for AI models. Basically, the attacker can embed instructions inside content that the model is expected to process, but then those instructions will be malicious. It can cause the model to behave in ways it was not intended to. The classic example here would be your images. You know, they typically have the alt attribute, the alternative text attribute. Instead of providing an actual text in that field, the attacker can embed a malicious prompt in there. So from the front end, all we see is an image, but on the back end, you have the malicious prompting working there. So it can tell the help desk agent to dump the customer database instead of resetting a password, all while appearing to be benign image metadata. So where does this threat live? Well, basically almost anywhere. It can exist in emails passed by your AI assistant, web pages, uploaded documents or PDFs, tool outputs fed into your AI model. Basically, any external content that your LLM read, they can be subject to a prompt injection attack. Now, there are ways to combat this, okay? First of all, we have policy filters embedded in the system prompt. Remember when we talked about system prompts, how you can set the tone, you can tell the AI model not only what to do, but not what to do. So we can say things like, hey, if you see any kinds of requests that handle files with certain tags like, user data, stop what you're doing, raise an alert. We can also say that, hey, reject any request to produce shell commands. Of course, this is obviously a very, very powerful task. Reject any kinds of requests like this unless the user role is that of an admin. And because of policy filters that we can embed in the system prompts, we can prevent privilege escalation and then also Policies can be evaluated on every request, not just at login, ensuring continuous access control throughout a session. The key note here is that your policy filters and your system prompts can basically act as the first line of defense. Now, we can also apply what we call guardrail frameworks. There's two of them. You have your OpenAI guardrails, which we will take a look at, and then your NVIDIA NeMo guardrails. These can act as protective layers between your user input and then the output produced by the AI model at the end. So basically, you'll have your user input, raw prompt received from the caller. You'll have your model that will process the raw prompt. The draft response will be created. And then you'll have your guardrail inspection, checks against your JSON schemas and rejects allowed lists. And then safe response, basically only validated, properly formatted output will be returned by the AI model. Now, we also have watermarking and signed responses. Basically, cryptographic watermarks are hidden markers embedded in model output that are difficult to forge or remove. They enable downstream systems such as your SIEM platforms and your instant responders to verify that a response genuinely originated from an authorized AI model. So basically, we can embed these cryptographic watermarks in the responses generated by AI models so that the other tools like your SOA, your SIEM, when they receive that output and they're able to see that watermark, they know that, okay, yes, this truly came from the AI model. So they basically act as verification process and then, of course, ensuring accountability as well. Now, there are other ways by which we can protect our AI systems: rate limiting and exhaustive audit logging. So by rate limiting, we can throttle at the API gateway, and this can slow brute force prompt probing, raising the cost of an automated attack campaigns significantly, okay? And then, of course, audit logging. Every single request and response will be captured with timestamps, user identifiers, and source IP addresses for forensic reconstruction if needed. And then we can also establish a forensic timeline. Because of the detailed logs, they will allow incident responders to trace any kind of suspicious activity and reconstruct attack chains end to end. Basically, you can think of all of these as defense in depth. Okay, you have your system prompts, you have your guardrails, you have rate limiting, you have your watermarks, and so on and so forth. Now, before we close, I just want to show you something real quick, deploying your OpenAI guardrail. Again, keep in mind that the guardrail basically inspects the inputs and the outputs. It sits at the intersection between the user, the caller, and the AI model. You can think of it as kind of like a firewall that is monitoring traffic between two networks, one internal and then one external. So basically, you can insert your guardrail system as a reverse proxy. So it sits in between your application and the AI model. So it can route traffic. We send requests through the local reverse proxy. The guardrail review, basically, it inspects all interactions and enforces policies. And then any kinds of logs or connection requests that are blocked will be recorded. And prompt engineering as DevSecOps. Prompt engineering applies the same rigorous engineering discipline to language that DevSecOps applies to compiled binary code. Security is not an afterthought as it is built into every layer of the AI interaction model. So again, remember that your system roles can be defined with the system prompts. They can act as formal security policies, defining the model's responsibilities, permissions, and hide boundaries. And then your user prompts provide tailored, scoped instructions that can guide the model on specific tasks without granting unnecessary authority. So, key takeaways: your prompt security equals injection defense. Hostile prompt inputs must be treated with the same severity as SQL injection in web applications and databases. And then your policy filters can enforce access at inference time. Your guardrail frameworks inspect both directions. Again, remember, it inspects the data coming from the AI model to the caller or from the caller to the AI model. And then cryptographic watermarks can verify provenance. Your rate limiting plus logging can equal forensic readiness. And then guardrails essentially act as reverse proxies. Thank you for watching. I will see you in the next class. Let's move on to section 4, one of the more important sections throughout this entire course. Funny enough, it's also one of the shortest, but in here, we're talking about securing AI data. And why do I say this is very, very important? It's simply because data is the lifeblood of AI. You can talk about security, you can talk about training, you can talk about anything else, but at the end of the day, data is the single most important and also the most powerful component of any AI system. So in this section, it's all about how can we protect that data. It is vital. So we're going to talk about data security related to AI, why data is AI's biggest attack surface, and then the data security considerations, okay, your CIA, the CIA triad, confidentiality, integrity, and availability, and then the different types of data types in AI, all right? We have, of course, the training data, the inherence data, the output data, and each of these types also have their own unique vulnerabilities, which we'll take a look at. And then the data handling techniques. How do we actually handle data in a secure manner? So classification, minimization, anonymization, and so on. We're going to take a look at all of that. So by the end of this section, you will be equipped to identify data level threats across the AI lifecycle and apply security controls at every single stage, a critical skill for any AI security professional. Let's get to it. Let's now move on to data security related to AI. And the point here is to understand how data security applies in the context of AI systems. Now, obviously, we are living in the age of AI. We have companies, organizations, and even law enforcement who are now integrating AI into their operational workflow. So as a result of this, we need to make sure that the data with which the AI works with is secure at all times. I have said this before and I will say it again. Think of data as the lifeblood of your AI systems, okay? Good quality data, training data means that your AI systems will be very, very efficient. And because AI, we now use AI to protect our data, we need to make sure that we're also protecting the AI itself. Because guess what? If hackers and cyber criminals are able to compromise our AI systems, the very systems we're using to protect our data, eventually our data themselves will become corrupted or could be stolen. So the role of data processing specifically, effective data processing will be the backbone of data security in AI, and ensures that data at all times is securely collected, stored, and transmitted at every stage, directly reducing the vulnerabilities introduced across the data life cycle. So in every stage of the data life cycle, from the moment it is created or stored or transmitted, there are always vulnerabilities at each one of these stages. So when it comes to collecting data in the first place, we want to make sure that the data has been collected from sources that have been validated. We know who the source is for this particular data. And then, of course, when we store that data, it has to be encrypted. Encryption is very, very important. And then when we're transmitting that data, we transmit it across channels that have been protected and also have the integrity verification. Now, obviously, AI for defensive security, it has a lot of advantages. One of the key advantages of applying AI in defensive security is that we're now able to reduce threat detection basically from hours to minutes or even seconds in certain kinds of cases. However, this particular boost in speed, the speed advantage, is again only as reliable as the data powering it. Again, I'm going to stress this one more time. When you have high quality data powering your AI systems, they're going to be far more effective. So secure data processing will directly enhance the training data quality, mitigating risks from poisoned data sets and manipulated model outputs. All right, so risks and regulatory requirements. The key risk here is that vulnerabilities in your data pipelines can turn the very tools designed for protection into active threats against the organization. Again, We use AI to protect our data, protect our systems. But what now happens when hackers and cyber criminals actually now take control of that very AI system itself? So regulators are responding because of this. So new AI-focused frameworks now mandate controls that go beyond traditional cybersecurity boundaries. So we do have 3 regulatory requirements for AI data security, and please take note of this for the exam. The very first one here is the data provenance controls, where we basically track the origin and lineage of the data used with AI systems. The algorithmic transparency, basically explaining the model decisions. There needs to be an understanding of why the AI systems made certain kinds of decisions. However, I do need to add a caveat here. The thing is, it has been shown, it has been proven that the more sophisticated, the more effective the AI systems are, especially the deep learning models, the ability to explain the decisions gets increasingly more and more difficult. So the point I'm trying to make here is that this algorithmic transparency, it's a very gray area. There are certain situations where it might be impossible to have full transparency. I'm just letting you know that. And then ongoing monitoring and then post-deployment, which means basically that all AI systems that we use need to be constantly monitored even after they have been deployed. So some key takeaways: AI, it is an evolving discipline, okay? We're still in the very early stages of AI. Think of AI in the next 10 years. That's going to be something else. So AI data security sits at the intersection of cybersecurity, data engineering, and risk management, and continues to evolve as threats and systems mature. Obviously, right now, the main AI attacks tend to be, prompt injection, adversarial prompting, and so on. But as AI systems evolve, become more and more sophisticated, guess what? New kinds of vulnerabilities and risks will arise as a result. And then, of course, resilience by design. Well-designed and effectively managed AI systems are inherently audit-ready, resilient, and adaptable to shifting operational and regulatory conditions. Thank you for watching. I will see you in the next class. Let's now move on to the next lesson. And here we're talking about data security considerations for AI. All right. So the very first thing we need to ensure Let's now move on to the next lesson, and here we're talking about the data security considerations specifically for AI. And the very first thing to consider would be the data pipeline hardening, okay? Again, I've said this before, I said it in the last class, data is the lifeblood of AI systems. So we need to make sure that at all times, the data the AI systems is working with or being trained on is safe and secure. We need to basically ensure that we verify the integrity of the data. So confirm the data is complete, accurate, and traceable to its source before AI ingestion. Before we provide any kind of training data to the AI, we want to make sure that, yes, we know the source of this data, it has not been corrupted, and it is free of any kind of malware. And then clean and standardize. So remove bias-inducing inconsistencies to prevent skewed AI outputs. And then, of course, encryption at all times, both when the data is in transit and when the data is at rest. Now, there are basically 3 different types of data: structured, semi-structured, and unstructured. We will talk about that in the next lesson. But each data format carries unique risks when feeding AI systems. Now, if you're talking about your structured data, this typically would be data you get from your intrusion prevention systems, your firewalls, and so on. So these basically can reveal operational techniques, shift schedules, and even the attack surface timing. Those are the vulnerabilities associated with structured data. But then we also have the semi-structured data, basically any kind of data in JSON output, your email headers, your YAM, may embed authentication tokens or even passwords. So this would require automated scanning and sanitization. And then for your unstructured data, this could be your packet payloads, chat transcripts, images from your camera. These can expose employee names, defensive techniques, and facility layouts. Please understand and know the vulnerabilities or risks with each and every one of these three different types of data in AI security. So besides the data pipeline hardening, another thing we can consider would be the application of dataset and model watermarking. So watermarking embeds invisible identifiers into AI generated content, establishing ownership, ensuring integrity, and of course, enabling legal protection. So when we have watermarks embedded into the AI generated content, that can obviously help with security. So with data integrity, we can track data through its life cycle, detect tampering that causes hallucinations, and then of course the legal standing. When we have watermarking, this can demonstrate clear ownership in copyright or content usage disputes, and of course model protection. Unique test prompts will produce recognizable outputs guarding against duplication or reverse engineering. So needless to say that if we're able to watermark our models, our data sets, this can go a long way into ensuring security. And there is also this issue of RAG. We've talked about RAG already several times. RAG pushes fresh knowledge into vector storage while keeping the foundation model unchanged, eliminating costly retraining after every document update. So again, the key advantage of RAG is that it allows AI systems to update themselves to produce information by pulling that information from external sources. However, the vulnerability or risk here is that these same RAG systems, they may end up storing very large volumes of information that is private, that is sensitive, and as such requires dedicated protection. So there are three key ways to protect against any sort of RAG compromise. The first one is to encrypt the vector index. So basically, we protect the database of numeric fingerprints at rest. And then something that we call the tenant isolation. Basically, we're making sure that departments are prevented from being able to access each other's priority data. So think of your large organization. You have your marketing department, your Q&A department, your HR department. These will be separated, okay? So one department will not be able to access the data of another department. And then, of course, the sanitization of inputs, block prompt injection attacks before queries even reach the model. So these are the three ways to protect RAG. And then overall, when you put everything together, the four key data security considerations, you have your pipeline hardening, so we secure ingestion, validation, and access controls. You have your data type awareness, again, structured, unstructured, semi-structured. We'll classify the sources and apply the tailored protections, watermarking, and of course, application of secure RAG architecture. So disciplined data stewardship across all four pillars will ensure AI-driven cyber defenses remain reliable, trustworthy, and resistant to adversarial manipulation. So key takeaways: AI obviously amplifies defense, but also amplifies risk as well. So data fueling AI, again, must be protected with the same rigor as any critical asset. Every data type has its unique vulnerabilities, whether it's structured, semi-structured, unstructured. They all require tailored controls. And then watermarking plus RAG security are a non-negotiable. Thank you for watching. I will see you in the next class. Let's move on to the next lesson, and this is going to be data types in AI. It's going to be a very short lesson, but this is something you do need to know for the exam itself. So, like I discussed in a previous lesson, we do have three different types: structured, semi-structured, and then unstructured. Now, think of structured data as like the gold standard for any kind of organization because, well, it is actually structured. So, using the library as an analogy, okay, if you were to walk into any decent library, every single book has been shelved using either the genre, the category, the name of the author, maybe even the year it was published, and so on. So basically, there is a very clear structure that will guide you into being able to locate a specific book you're looking for rather quickly. So structured data, they follow a very rigid schema, right? A strict blueprint will define the format of every single entry. And then, of course, each field must conform to a predefined type with no exceptions, no surprises. So a very, very rigid and strict schema, highly organized as a result. And of course, because the data is structured, machines love working with this kind of data. The structured data is easily searchable, sortable, and interpreted by machines with minimal pre-processing. Okay, next comes the semi-structured data, the sweet spot. So over here, it sits in between, of course, structured and unstructured. So we do have some organization. Basically, with semi-structured data, they tend to use tags. So they'll use tags and markers to provide some structure. However, the structure still isn't quite as organized or as rigid as that of the structured data. So common formats, of course, will be your JSON, your JavaScript object notation, which is, of course, widely used by web applications, APIs. And then, of course, your XML files, your extensible markup language, and, of course, HTML, which is basically the markup behind all web pages. Now, it is flexible because a record, any particular record under the semi-structured data, might have many data fields or just a few, but the schema itself is self-describing, meaning that the data itself carries its own organizational hints. Okay, and of course, last but not least, we do have the unstructured data. Going back to the library analogy, it is basically the back room where the returns have been dumped, they have not yet been sorted, nothing is labeled, and finding a specific book could be a very serious challenge. And yet, despite the fact that unstructured data might just seem to be the least desirable kind of data, it is the most abundant form of data in the world. Okay, so very, very funny about that. But basically, your text, images, audio files, video, social media posts, none of these have any kind of predefined format or schema. So when you think of unstructured data, think of your social media posts, audio files, videos, and so on. So it is, of course, the most common type. Estimates suggest over 80% of all data in the world is unstructured. And guess what? It's only going to grow much faster. And it can be very hard to process. Standard database tools cannot interpret it. And of course, it also needs deep learning. So powerful AI techniques like deep learning models and neural networks are required to find patterns and extract useful insights. So key takeaways: understanding data types is foundational to understanding how AI works. And then, of course, organization equals efficiency. So if you're working with your structured data, it's going to be very, very efficient. But complexity scales with chaos. So as data becomes less structured, more powerful and more resource-intensive AI techniques will be needed to be able to actually work with the unstructured data. And then know your data first. Okay, so before building your first AI system or any AI system, understanding what type of data you're working with will be a critical first step that will shape every single decision that will follow in the development of that AI model. Thank you for watching. I will see you in the next class. Let's round up this module by talking about the different data handling techniques. All right, so AI and cybersecurity basically has always been a double-edged sword. In much the same way that we have the good guys, the security professionals using AI to protect systems and networks and data, we also have attackers who use AI for enhanced cyber attacks, such as, automating reconnaissance, crafting convincing phishing campaigns, and probing defenses at machine speed. Now, when it comes to the data lifecycle with AI, you have the data being processed, and as such, we need to ensure that its integrity is assured at all times. We have verification as well as lineage tracking. So each stage introduces distinct opportunities for both improvement and exploitation, security must be embedded at every single step. So when it comes to data processing and cleansing, this is one of the techniques for securing data. Here, we're basically removing any kinds of copies or duplicates. We fill any missing values and resolve contradictory entries. As such, we ensure that algorithms will learn from accurate signals and not just empty noise. So as an example, you may have a SOC aggregating firewall logs, which may misclassify legitimate traffic as malicious, lateral movement, if the IP addresses lack any kind of subnet masks or time zone metadata. We also have, of course, data verification. Now, there are several ways we can ensure this. One is through the use of the cryptographic hashing. In fact, I will say this is probably the most common. Basically, you will generate a hash for every ingested data set. And of course, we'll store the hashes in a trusted read-only location. And of course, the use of command line tools like your SHA-256 sum for Linux or get-file hash in your PowerShell for Windows. And these can detect even the smallest changes in the data, so great for data verification. And of course, your CI/CD integration, so GitHub Actions, GitLab CI, and Azure pipelines support hash verification natively, failing jobs on mismatch. Let's move on to data lineage and provenance, another very important step in data handling. So in data lineage, this will record every transformation a dataset undergoes, which is essential for auditors and ethics boards. So basically, anytime we make any kinds of modifications to the data set, whether it's being updated, whether we're adding new kinds of data or editing or moving data, we need to make sure that it is all recorded. And then data provenance documents origin, licensing, and consent terms. Pipelines must scan for PII and copyrighted material before use. Very, very, very important. And then, of course, your LLM and your RAG scenarios. So we can save the source URL, the timestamp, the content hash, and license, enabling rapid removal of tainted data before it even spreads. Now, specifically, the tools under data lineage and provenance, you have your AWS Glue data catalog, as well as the open source Apache Atlas, which will automatically capture lineage metadata at scale. Data integrity itself, the safeguards we use for these will include digital signatures, and this will ensure that data arrives exactly as it is sent. It has not been modified. It has not been tampered with in any way. So in regulated environments, an append-only blockchain will create an immutable audit trail. Now, as an example, in fact, we have two of them in here. We have your hospitals and universities. So in the hospitals, in the medical clinics, they can sign and hash MRI archives and record them on a consortium ledger. And then universities can auto verify signatures before any sort of federated learning. So any mismatch in here would halt processing and will trigger an alert as a result. Now, when it comes to data augmentation, of course, this generates additional training example. So you have rotating images, flipping sequences, adding noise to help models generalize and resist adversarial attacks. So by adding just a little bit of noise to the training data set, this can help AI models fight back against any sort of adversarial prompting or attacks. The benefit here is that it will prevent overfitting and will strengthen the robustness against adversarial attacks. But then the risk here is that we can also embed hidden biases or leak sensitive features. So synthetic data must be properly tagged for traceability. And then the concept of data balancing. When you have your imbalanced data sets, this will end up skewing our AI models to make very biased decisions. So as an example, in your intrusion detection system, if 99% of the flows are considered to be benign, your unbalanced classifier basically in this scenario labels everything as safe. And as such, we can actually have real attacks, real threats that go unnoticed. So in this particular kind of scenario, we can introduce the concept of data balancing, which would realign the training sets so that rare, critical, and rare events that rarely ever happen, they would also receive proportionate attention as a result. And then the application of behavioral analytics and continuous monitoring. We want to identify anomalous workflows, for example, any sort of unexpected spikes in training set size might signal a poisoning attempt because of obviously the attacker right now is adding extra malicious data to corrupt the training process. And then of course, NLP metadata inspection, natural language models, they can scan data, catalog metadata for compliance, violations automatically. So the key takeaways for this lesson, we want to cleanse and verify. So basically, of course, sanitize the inputs, sanitize the data, remove any sort of duplicates, unnecessary noise. So remove noise and cryptographically confirm dataset integrity before any kind of training. We want to track the lineage and provenance of the data. We want to make sure that integrity and balance, the training data balance, is ensured at all times. So we can use digital signatures, immutable ledgers, and balanced data sets to prevent bias and contamination. And of course, monitor continuously. Behavioral analytics protect AI data pipelines from poisoning and compliance violations. Thank you for watching. I will see you in the next class. Welcome to Module 3, the third main domain in the CompTIA SecAI Plus training. And here, well, all right, so welcome to Section 7, which actually marks the... So welcome to Section 7, which is actually the start of Module 3. And over here, we're talking about access control for AI. And in many ways, AI security shares a lot of similarities with your traditional data or system security because we also do have access control for AI. Who can use the AI? What can they actually do with the AI? And how do we stop unauthorized users from being able to gain access to the AI? So we're going to take a look at the principles and models behind access control specifically for AI security. We'll take a look at the AI threat landscape. We will discuss different kinds of threats like data poisoning, prompt injection, and so on. And then take a look at the model, user, and data access, and then network and API access as well. So by the end of this section, you will be able to design and enforce access control architectures that actually protect our AI models, data agents, and APIs across any deployment environment. Let's begin. Let's now discuss the access control principles for AI. And if you've ever studied access controls in basic cybersecurity, it's pretty much the exact same concept in here. Now with access control, we're typically aiming to satisfy the CIA triad, where you have confidentiality, integrity, and availability. So it's the exact same thing with AI. We want to make sure that in terms of confidentiality, only authorized subjects can actually access the sensitive resources on the AI model. And then in integrity, we're making sure that the data with which the AI is trained on, or whatever data the AI processes, it has not been tampered with, it's not been modified. And then availability, we're ensuring that the legitimate users who have the necessary authorization to use the AI model are able to do so. That's basically what access control for AI is. Now, in the same concept, we have what we call the subjects and then the objects. The subjects, these would be people, devices, software processes, even applications that can request and be granted access to a resource. So subjects are typically assigned the rights or permissions. Basically, what can they actually do on the resource based on their identity, role, and context. So humans in this case right now could be just regular standard users. It could be the administrators, it could be the developers, it could be anyone. And then we also have automated processes and scripts that can utilize resources, and then devices, and then of course our endpoints. And then objects would be the actual resources that are being accessed and processed. So in an AI environment, objects take on unique forms that would go beyond just your traditional file systems. In this case right now, the resources could be the AI models and the model weights. It could be the training and inference data sets. It could be the prompts and prompt templates, the API endpoints and output logs, all of this being unique to AI systems. We also have identity and access management, where we discuss identification, authentication, authorization, and then, of course, accounting. So these four processes, they work in sequence and in concert. Each layer will build on the previous to create a robust auditable access control posture for AI and enterprise systems alike. So let's take a look at them one by one. Obviously, we have identification and then authentication. So identification will simply be the process of actually creating an account name or some form of identity that would uniquely represent either a user, a device, or maybe even an application within the system. So it is typically the very first step in establishing who or what is attempting to access a resource on the AI model. So every subject in an AI environment, from a developer to an automated pipeline, must have a distinct registered identity, and it must be distinct to ensure auditing and accountability. Now, authentication, the AUTHN. So this is the process of basically proving that the subject is who they claim to be. Okay, so an authentication factor determines what credential the subject presents, such as a password, a token, a digital certificate, biometric, and so on. So stronger AI environments will require multi-factor authentication to reduce the risk of credential compromise. So again, it's just like your traditional file access control. Maybe you're trying to log into a particular system. You need to prove who you are. So you might need to provide some sort of like a username and a password, and then maybe also use a physical device before you can be granted access. So that's basically authentication. I am who I claim to be. And then we have authorization. Now, authorization will determine what permissions, the kinds of rights that the subjects will have access to once they have been authenticated. So basically, you authenticate saying, hey, I am who I claim to be. I have proven my identity. Now, authorization will assign my permissions. What can I actually do? Can I create new kinds of files? Can I modify existing files? Can I delete them? Can I transfer them? Can I download them? And so on. So we have different kinds of roles when it comes to authorization. We can have your typical AI end user, so limited to submitting prompts as far as AI is concerned. And then we can have the AI engineer, obviously more powerful. Here they can redivide access to model configurations. And then, of course, we have the AI system admin who will have full administrative access to the AI model. And then, of course, accounting. This will track all authorized and unauthorized usage of resources by the subject. So we typically will have to log every single kind of access or interaction with the AI model, alert on authorized access attempts, generate audit trails for regulatory compliance, and of course, support incident response investigations. And then we also have access controls that are specific to AI systems. In this case right now, we have what we call the multi-actor access boundary. So controls must govern interactions for users, engineers, and the AI model itself, each requiring different scopes of access to data and then the system components, and then the sensitive data protection. Don't forget again that AI systems would work with very, very important data. So the data sets typically would contain your PII, your PHI, and possibly even financial records. So fine-grained access controls must ensure that these categories are only accessible by those who have been authorized to do so. Basically, we're ensuring confidentiality. And then the principle of least privilege. Again, just like with your traditional file access control, we should only grant the minimum access required to perform a particular kind of function. So this would limit the blast radius in the event of a compromise, okay? If you, as the standard user for an AI model, you only need to be able to send prompts, then that's all you should be able to do. You should not be able to begin to access the code behind the AI model as an example. So key takeaways, understand your AI access control mirrors enterprise standards. You have your subjects and your objects. And of course, the 4 core processes of your IAM: identification, authentication, authorization, and then of course, accountability or accounting. And then of course, least privilege for AI data, very, very important. So for the exam, please understand the difference between authentication and then authorization. Again, authentication is basically, hey, I am who I claim to be, and this is the evidence, okay? And then authorization basically will give the user the privileges or the authority that has been assigned to them. So these terms are frequently tested on the exam, so make sure you know them. Thank you for watching. I will see you in the next class. Let's now move on to access control models. All right, so we have the principle of least privilege in AI. So basically here, every user and every system component will receive only the minimum amount of privileges, the minimum amount of access or authorization that they need in order to get their tasks done. Nothing more, nothing less. In this case right now, we can limit it to the model. So with models, we can limit which users or agents can invoke or modify the AI models. When it comes to the data, we can restrict data set access only to those who have the authorization to access them. And then, of course, the APIs, we can limit permissions to access the APIs. And then, of course, agents, okay, we can constrain autonomous agents to approved actions and resources. We also have threats reduced by proper access control. So when we have proper access control, we basically limit the unauthorized access, obviously, and then model exploitation and abuse. We can block malicious prompt injection and API abuse attempts that would aim to extract sensitive information or manipulate the model behavior. And then we can also prevent denial of service, thereby ensuring availability. Now, when it comes to role-based access control models, your RBAC, this will grant permissions based on a user's or system's defined role within the enterprise. So access will not be given directly to the users. However, it will flow from the role they occupy, making the administration scalable and then auditable. So the whole idea here is that we can create roles, okay? You can have the role for a standard user, a role for a supervisor, a role for an engineer. So instead of creating, unique roles for each user, we can just create this one role and then assign that role to as many users as we want, provided those users match that particular role that we've created in terms of the levels of permission. So we can have standard users. So here we can access will be limited to specific models or even data and approved prompt interfaces needed for day-to-day job functions. So this would be your typical standard user, but we can also have supervisors and admins who will have more privileges, much more control and power over the AI models. So under RBAC, we have, of course, the attribute-based access control. So ABAC, this goes beyond organizational role, using attributes attached to both the both user accounts and data resources to determine the precise access level. So in this case right now, we can have the user attributes. So here, properties like your level of clearance, your department, your employment type, and so on, or even your geographic location can determine what a user can actually access. So those would be the actual user attributes. And then we have resource attributes. So data and model resources can be tagged. For example, we can have a data resource that is confidential, that is public, that is restricted, and so on. So access will be granted only to those users who actually have the right kinds of attributes to access them in the first place. And then we can also have granular inference control. So permissions here can separately govern model use, model retraining, and inference, each controlled independently. Now, as an example, we can have an AI researcher, a developer, may have access to all the data sets, okay, obviously because they're a developer. However, an external contractor will see only data that has been explicitly marked as public, enforced automatically through attribute matching. Okay, next, of course, will be data privacy and regulatory compliance. So access control design in AI systems must account for applicable data privacy regulations. Obviously, of course, again, GDPR, if you're based in Europe, That's something you need to account for. HIPAA, if you are in the medical industry, that's another standard you have to adhere to. And then the Privacy Act of 1974 governs federal agency handling of personally identifiable information, requiring access limitations and audit trails for government AI deployments. And then policy as code. What exactly is this? So over here, rather than you relying on standard procedures or static stale documentation, modern AI systems can actually implement access governance through policy as code, which is basically expressing or enforcing policies programmatically within the development pipeline. So what are we talking about? You have some key tools in here. Your Open Policy Agent, your OPA. Know this for the exam, by the way. This is open source, general purpose policy engine. We can have the AWS IAM. This will be your cloud native identity and access management. Your Azure policy, governance across all Azure AI resources. And then, of course, your IBM Watson, AI-specific policy enforcement. The core benefits of using the policy as code is that you can have, of course, centralized control, which is, of course, always easier to manage, auditability, and then automated compliance because regulatory requirements will be embedded directly in your CI/CD pipelines. And then API access controls. Obviously, you need access controls for the APIs as well. So APIs are the primary interface layer of your AI services. So securing them would require a layered set, defense in depth, set of controls that will govern who can actually connect, what they can send or receive, and how interactions are recorded and filtered. So over here right now, of course, you have the typical rate limiting, input and output validation, your audit login, content filtering, and then context-aware controls where we dynamically adjust permissions based on real-time factors, such as the time of the day, the device being used, the geographic location, and so on and so forth. So key takeaways: least privilege is non-negotiable. Very, very, very important. You can have your role-based access control or your attribute-based access control depending on the organization. And then compliance will be embedded, not bolted on. API controls are the last line of defense. And don't forget, your first line of defense are what? Your guardrails. Thank you for watching. I will see you in the next class. Let's now move on to threat landscapes of AI systems. Now, we do obviously have different types of threats to our AI models and systems. We do have internal threats. Now, I do need to point out that the typical default explanation of insider threats would be, disgruntled employees who are not happy, who then deliberately misuse the AI model. But I also do need to point out that sometimes the internal threats could be from regular employees who are simply either poorly educated or naive or careless. Okay, so internal threats could either be deliberate or accidental. I want you to keep that in mind. Then obviously we do have external threats. So malicious actors outside the organization may launch DDoS attacks. We do have natural threats, like bad weather, fires, flooding, and so on. So these, of course, can cause unplanned AI system downtime. And of course, man-made threats. So users may deliberately craft misleading prompts or inputs designed to cause the AI system to produce inaccurate, biased, or harmful outputs. Now, when it comes to data manipulation and poisoning, of course, this is one of the biggest threats because, again, data is the lifeblood of AI systems. Now, when you corrupt the data that's been used to train the AI model ends up being biased and, quite frankly, useless. So, because AI models learn directly from the data they're trained on, poison inputs can silently degrade the model long before the damage is even detected. And of course, incorrect training data can occur sometimes. Sometimes data manipulation and poisoning may also be accidental. And then bias manipulation. A more subtle attack will strategically skew the training data distribution to push the model towards a particular kind of opinion or classification, which will of course end up with the model producing biased outputs. So Identifying threats to AI systems obviously would be far more complex than your traditional IT systems. Obviously, AI applications and models are far more complicated, far more sophisticated than your typical computer system. So AI models operate as layered, probabilistic systems that can be difficult to audit. So unexpected outputs may result from subtle data issues rather than obvious configuration errors. And then we also do have frameworks and standards. So threat identification frameworks and internal standards will give organizations structured methodologies to systematically surface, assess, and manage any sort of risks that are specific to their AI systems. Now, when it comes to the standards for threat management, we do have the ISO standards. These are key. So the three main standards in here would be your ISO, your IEC 27001, 2022. This is for information security management specifically. So we also have the ISO IEC 42001, 2023. This is for your AI management systems. And then the third one is your ISO IEC 23894, 2023. This is specifically for the AI risk management. We also have, of course, the OWASP Top 10, which we've already talked about. This is an industry-recognized list of the top 10 most critical security vulnerabilities affecting AI-powered systems. Examples would be your prompt injection, data model poisoning, sensitive data exposure, misinformation. We've already talked about this in a previous lesson. And then, of course, your prompt injection attacks. We cannot ignore these particular kinds of attacks. So it all starts with a benign query and then follow-up manipulation, which may end up with the exposure of sensitive data. So this incremental escalation will exploit the AI's stateful conversational context. Each step appears individually reasonable, but then the cumulative effect could end up causing the system to cross security boundaries, exposing account names, credentials, or other protected data to an unauthorized user. So key takeaways in here: multi-vector threat exposure. Obviously, AI systems face threats from multiple factors and vectors. Data poisoning can be a very silent risk. We do have the ISO standards for governance. We have the OWASP Top 10, which guides prioritization of security vulnerabilities. And then prompt injection will exploit conversational context. Thank you for watching. I will see you in the next class. Let's now take a very quick look at model access. So what is AI model access? Well, as it clearly suggests, it basically defines the boundaries of how different users can interact, use, or control an AI model. So typically you would have two different kinds of users or levels of access. You will have the typical user access, the standard user who can create prompts. They can ask the AI to do certain kinds of things. However, they will not be in a position to alter the way the AI behaves, its parameters, or its training data. And of course, you will have your developer admin access, who will have far more control over how the AI model operates. So controlling model access, again, this will depend on authentication mechanisms. So access to AI models is protected using standard authentication methods, such as API keys, your tokens, multi-factor authentication, and so on. We also have the authorization levels as well. Hey, are you authorized to do certain kinds of things? Do you have the authorization of a typical user, a standard user, or do you have the authorization levels of a developer? And then, of course, the use of rate limiting and request control. So access can also be controlled by limiting the number of requests a user or an API integration can make within a given period of time. We've already talked about this previously. And of course, logging and auditing model access. So every request made to an AI model should be logged in detail. This will ensure auditing and accountability. So these logs will form the evidentiary backbone for any future security investigation or compliance review. And of course, regular auditing is also necessary. Logs alone by themselves will not be sufficient. Regular audits must be conducted to verify that access patterns do align with established policies. And of course, auditing will detect any kinds of anomalies, unauthorized access attempts, and so much more. So key takeaways in here: model access, we've defined what it is. The user access is scoped based on the levels of authorization. We do have elevated developer and admin rights. Authentication and authorization are necessary for model access. And of course, logging and auditing would also be required. Thank you for watching. I will see you in the next class. Let's move on to data and agent access. So data access control, again, this will control which users or entities will have access to an AI system and what it is that they can actually do. So the most effective approach ties access rights directly to organizational roles, ensuring each user can only see the data relevant to their function. So as an example, you may have an HR employee who would require access to records of the employees, the compensation history, disciplinary files, and so on. But then you could also have a finance employee who will need access to time cards and pay rates. So sensitive HR records outside the operational need would be off limits, reducing exposure risks. So basically, you're only granted access to the kinds of files that you actually need. Other kinds of files not related to your role or your department, you're not going to have access to them. Now, we do need to discuss the differences between agents and tools. Now, agents, when talked about in the AI perspective, these are systems, okay, that can perceive their environment. They can reason about goals. They make decisions and even act autonomously. They can make decisions on their own. So agents can also control which APIs and other agents will interact with specific portions of a data set. So needless to say that agents can be very, very powerful, but tools are passive components that will perform very specific kinds of tasks when explicitly instructed by the agent. So you can think of agents as performing tasks through the use of tools. So tools do not act on their own. Instead, they will respond to commands, making their scope or influence more predictable and contained. Now, because agents, like I said, can be very, very powerful, they can make decisions, they can act autonomously with elevated access to systems and data, they are classified as privileged execution surfaces. And because of this, the kinds of access controls go far beyond the standard user access policies. So obviously, we need to make sure that whatever kinds of data are handled by our agents, they do satisfy regulatory compliance. Obviously, we also need authentication and encryption. So many organizations will require MFA and data encryption at rest and in transit for all model and data access operations. And of course, documentation and auditing will be necessary as well. So recommended controls for agents and tools, we do have the explicit allow lists. So over here, we can grant granular permissions, which will define exactly which tools each agent may access. And then every other attempt, every other agent or tool, we're going to deny them access by default. And then, of course, secret expiration. So time-limited credentials and tokens will reduce the window of opportunity for abuse or unauthorized access. So we're going to make sure that agents or tools will have access to certain kinds of data, but only for a limited number of time. And then, of course, data anonymization. Personal identifiable information, PII, will be masked or de-identified to, of course, satisfy compliance regulations. And then the use of network access control lists. So access control lists will govern which systems, agents, and tools can communicate with limiting lateral movement. Of course, we're going to deploy logging and monitoring and also the human in the loop. So any kinds of critical decisions that need to be made, we're going to make sure that a human actually approves them, and we just don't leave such decisions to the AI system. So key takeaways, obviously, role-based data access. Users and entities should only access data relevant to their organizational function. Agents are active, tools are passive, agents are privileged execution surfaces, and of course, regulatory and technical controls will be needed to ensure that agents and tools are used appropriately. Thank you for watching. I will see you in the next class. Let's move on to discussing network and API access. So, network and API access controls in AI environments. Let's move on to discussing network and API access. Now, it is important to understand that the kinds of AI systems that we use today, they typically depend on both internal and external networks. So you may have your AI model connecting to cloud resources or even the Internet of Things devices all across the globe. Now, obviously, with the use of APIs, your application programming interfaces, these AI models can communicate with these external services. Now, the more services they can actually integrate with, the more they will be able to do, the better the outputs will be. But guess what? Naturally, the more integrations they have, the more of these services they connect to, the more potential attack surfaces will arise as a result. So we do have threats from insecure network data. So when data travels between AI systems and external APIs, it may pass through networks that are not encrypted or fully secured. So this obviously would create a meaningful risk where if an attacker was able to intercept the transmission of data across that unsecured network, then they might be able to retrieve the contents of that data. So access controls must be elevated to compensate relying on perimeter security alone is insufficient in distributed AI architecture. So both users and communicating devices would require additional layers of authentication when data traverses untrusted or partially trusted networks. Now, obviously, when we do have the insecure networks, the kinds of key threats to watch out for would be eavesdropping, your standard classic man-in-the-middle attacks, data injection through unvalidated API responses, device impersonation, and of course, replay attacks using capture tokens or credentials. So how can we combat this? Well, we can also deploy authentication controls specifically for network systems. We do have 3 layers in here. One will be to, of course, enforce HTTPS communication. This will ensure that all data passing through the network will be fully secured. And then specialized one-time use tokens. So we can also create tokens that are meant to be used for one single session or one single request. Even if that token was captured by an attacker or a cyber criminal, they will not be able to reuse it because, again, it is for a single session and it has already been used. And then input validation, obviously before execution. All inputs to AI systems must be validated prior to processing. So together, these 3 different controls will mitigate the most common threats targeting network and API access in AI deployments. So we can also deploy or implement the principle of least privilege for our API access. So we can do this by minimizing the access depth, apply least privilege at grant and modification. So the principle of least privilege should govern both the initial granting of API access and then any subsequent changes to permissions over a period of time. And of course, we can also use firewalls and API-specific permissions. And of course, the multi-factor authentication for API access as well. 3 different types. You do have the basic authentication where you provide a username and a password, typically used alongside additional factors rather than alone. But we also have the certificate-based authentication. I would argue a bit more powerful because over here, we're making the use of digital certificates, which can cryptographically verify the identity of a client or service. And then, of course, the use of token-based authentication. Over here, advanced token mechanisms, including time-limited or one-time use tokens, can verify identity dynamically and also reduce the window of opportunity for attackers. So once identity is confirmed through authentication, next comes the authorization process, which will determine the actual kinds of permissions or privileges the authenticated user has access to. So key takeaways, again, expanded attack surface. The more services our API models integrate with, the bigger the attack surface. So we do need to enforce enhanced authentication, the principle of least privilege, and of course, multi-factor authentication. And for the exam tip, expect questions linking API access control to least privilege, injection attack mitigations, as well as multi-factor mechanism types. Know how each control maps to a specific threat. Thank you for watching. I will see you in the next class. Let's move on to section 8, applying data security controls and monitoring our AI systems. So over here, it's all about the different types of data security controls, things like encryption, masking, tokenization, and so on. We will discuss them in here. And then also, how can we monitor and collect logs from our AI systems? And we'll also take a look at auditing and compliance. So, general overview of AI data security controls, encryption of AI data. Obviously, we need to encrypt AI data when it is at rest, when it is in transit, and also when it is being processed, but also when it's actually being used for training. And then data safety measures as well, masking, redaction, and so on, prompt log and performance monitoring, and then the cost and compliance auditing. These are what we're going to learn in this section. So by the end of this section, you will have the skills necessary to be able to design, monitor, and audit security controls for real-world AI deployments. Thank you for watching. Let's begin. All right, so welcome to this brand new section. And over here, we're going to be analyzing the AI data security controls. So let's have a very quick walkthrough of what they are. Now, when it comes to the data protection mechanisms, there's three major types. We do have, of course, encryption. We have data masking, where you would replace sensitive values with anonymized or pseudonymous data. And then, of course, classification, where we can classify data based on the levels of confidentiality or sensitivity. Now, risk management from the perspective of improper storage and handling. Well, obviously, when you have the improper handling or storage of data, the inevitability is that you're going to end up exposing that data to people who are not supposed to have access to it in the first place. So we do have certain kinds of special handling requirements for very sensitive files like your PII and so on. And then we can also use the regulatory compliance programs as a ways to establish the handling requirements for these kinds of data. Now, when it comes to the actual process of classifying data, three main stages. First of all, we obviously need to identify our data assets. We need to be able to identify data that can be accessed by the public, data that is meant to be confidential, and so on. And then once we've identified those data, we can then apply the appropriate labels and clearance. So we say, this is public, this is private, this is confidential, and so on. And then, of course, we can then enforce the role-based access based on those levels of clearance or sensitivity. So when it comes to the regulatory compliance frameworks, again, we've talked about this several times already, but of course, for the exam, you do need to know them: your GDPR, your HIPAA, your PCI DSS, and of course, your government labels, which are typically three. You have confidential, you have secret, and then you have top secret. So please know those three. Obviously, security controls, these are the mechanisms we would apply to protect our AI data. And of course, well-implemented controls protect against three primary categories. We have, of course, accidental exposure, malicious data leaks, and then, of course, system bugs. So key takeaways in here for this very quick overview. We do have our core protection mechanisms, three of them: encryption, data masking, and of course, data classification. We obviously have risks of improper handling. This would lead to data exposure. Data classification, obviously, you need to know them. Again, remember that for the government, you have confidential, secret, and then top secret. Your key compliance frameworks, know them. And then, of course, purpose of controls will be to control or rather prevent accidental exposure, malicious leaks, and system errors. Thank you for watching. I will see you in the next class. All right, let's move on to the encryption of AI data. And of course, data, as far as AI is concerned, we have four different stages. We have data at rest, data in transit, data in use, and then data in training. So let's begin by explaining what data encryption is. You already know what this is, okay? Obviously, we want to transform readable or accessible data into an unreadable format. And the only way to actually read the encrypted data is by the use of valid decryption keys. Now, when it comes to the whole CIA triad, your confidentiality, integrity, and availability, encryption provides both confidentiality and integrity. So, data at rest. This is data that is lying, it's not been processed, it's not been transmitted. Three main ways to protect that data. We can encrypt the individual files, encrypt the folder holding the files, or encrypt the entire hard drive containing that folder and other folders. Also, when it comes to protecting the keys, the encryption and decryption keys, four main ways. We have your KMS, your key management service, controls access via access control policies. You have your TPM, very, very popular, the trusted platform module. Basically, it is hardware-based, tamper-resistant key storage. You have your HSM, your hardware security module, a dedicated device for cryptographic operations, and of course, your cloud KMS, your AWS KMS, and Azure Key Vault, which integrates with cloud AI deployment. So please know these four options for your key storage. Now, data in transit, data that's been transmitted, data being downloaded, uploaded, and so on. Three main ways, okay? We have your TLS, your transport layer security, your use of VPN, and of course, your secure protocols like your SFTP, FTPS, and of course, your HTTPS. These ones, you already know about them. But what about the HTTP3 and your QUIC? So, what exactly is QUIC? We call it the Quick UDP Internet Connections. It's relatively new, developed by Google. Now, what this does is that it's built on the HTTP3 is built on top of QUIC, replacing TCP with UDP for faster, lower latency communication. Now, the key advantage of using the QUIC is that the transmission layer itself already has your transport layer security on top of it. Okay, so basically, it's already built into the actual connection layer itself. It's not been layered or on top of it. So this will reduce the handshake overhead and would eliminate a class of downgrade attacks. So it's much faster. UDP-based transport reduces latency versus TCP. It is secure by default because it already has the transport layer security on top of it. And then it is, of course, the modern standard recommended for AI systems with high throughput data pipelines. What about data in use, data that's actually been processed? So we can use what we call the Trusted Execution Environment, your T. It is a hardware isolated region in your computer processor that can never be accessed by the operating system or the hypervisor. We have your AWS Nitro enclaves. These are isolated in compute environments for sensitive cloud workloads. And of course, the Azure Confidential Computing, hardware-backed enclaves for AI inference and training. And now we also have what we call the homomorphic encryption, your HE. How this basically works is that it would calculate, well, with mathematics, obviously, whenever encryption is involved, you have mathematics. So these mathematical operations will be performed directly on the encrypted text, the ciphertext, without ever actually needing to decrypt the data. So the result at the end of all those mathematical operations must match the output of the same operation on plain text. So this will eliminate the exposure window entirely. So data will stay secure all through computation to output. Now, machine learning, when it comes to data that's been used for training AI models, one of the key functions in here is to ensure privacy. Now, we can make use of something known as the DPSGD, the differentially private stochastic gradient descent. That is a mouthful, okay? So this protects individual data points used during model training, preventing an attacker from inferring whether specific records were included. So three main stages: you calculate the gradient, clip the gradient, and then you add noise. Now, let me explain exactly what this is, all right? As an example, let's say we're trying to train an AI model on how to diagnose cancer, all right? obviously we want the AI model to recognize the patterns of, of cancer, right? However, during the process of training, it is very possible that an actual individual private record, let's say a patient called John Smith, okay, it may be leaked to the AI model that John Smith has cancer. Now, obviously, we don't want the AI to remember specifically that John Smith has cancer. We want the AI model to learn from John Smith, learn the patterns of cancer from John Smith and other patients out there, but we don't want the AI model to remember specifically that a John Smith has cancer. So what we do here is that we calculate the gradient, okay? Measure each example's influence. Obviously, in this particular scenario right now, John Smith having cancer can have a huge influence. So we clip the gradient, we limit any single example's impact. We try to limit the fact that the AI knows that John Smith has cancer, or we can do so by adding noise, okay? We inject randomness to obscure contribution. So think of it this way, okay? We want the AI model to learn the patterns of cancer from John Smith, but we don't want the AI model to remember that John Smith specifically has cancer. We want to keep that information private. So we can add more noise. So the more noise we add to confuse the AI model, what happens here is that we have more privacy. However, when you add way too much noise, it may end up starting to now affect the way the AI model can actually recognize the patterns of cancer. So there needs to be a fine balance, okay? We need to add enough noise so that privacy is protected, but at the same time, the performance of the AI model isn't downgraded too much. Let me put it this way, okay? No matter how little noise you add, the AI's performance will downgrade as a result, okay? However, the levels of the AI noise itself, it can have a very, very minimal impact on the actual performance, okay? So again, the whole point here is that you add just enough noise to ensure that the AI's performance isn't downgraded too much, but at the same time, privacy is ensured. So a fine balance between the two. So key takeaways, your encryption fundamentals, know them, of course. Your data at rest, we can store the keys with KMS, TPM, HSM. Data in transit, we can use your secure TLS, your HTTP3, and secure protocols like your SFTP and so on. And of course, when it comes to data in use, we can use the homomorphic encryption, HE, and your TEE. And then, of course, with the DPSGD, we protect machine learning training privacy via gradient clipping and noise injection. And again, the trade-off here is that more noise will equal stronger privacy, but lower accuracy. So there needs to be a fine balance. Thank you for watching. I will see you in the next class. Let's talk about the data safety measures. And of course, risk is the potential for threats and vulnerabilities to compromise the CIA, confidentiality, integrity, and of course, availability. So AI systems themselves are not immune to these kinds of attacks. Risks do emerge from how they access, utilize, and store data throughout their life cycle. So obviously a data breach occurs when data is accessed or exposed to unauthorized users. There could be a variety of reasons as to why this might happen. Lack of encryption. You may have internal threats or external threats as well. So when it comes to model bias, again, this is something we've already talked about in the course. Model bias, it is a critical risk in AI systems, and it's of course where the AI ends up making a biased decision or biased judgment because of the data it has been trained with, flawed inputs. And when you have flawed inputs, you end up having flawed outputs, garbage in, garbage out. And of course, data masking, as we've talked about, it replaces real information with fictional but realistic values. Two main ways: we have static masking and dynamic. Now with static masking, what actually happens here is that the original data will never be exposed in a copy. So we're going to create a separate data set where the masking values, they will be applied permanently. But with dynamic masking, the masking occurs in real time. So it masks data in real time as it's accessed or used. then returns to its original value at rest. So the source data set itself, it's never permanently altered. Other ways to protect our data, we have anonymization, redaction, and then minimization. These three you need to know. So with anonymization, we remove identifying details from a data set. As an example, if we only need to know the month, the birth month of a particular user, then we can remove the day the person was born as well as the year. We leave only the month. So this will make it very, very, very difficult to actually identify who that individual is. Now with redaction, we remove or obscure or mask data that is no longer necessary after collection. Okay, so it's typically applied post collection. However, minimization, we collect only the bare minimum data needed for a task, and this is typically done before or during collection. Now, for the exam, you need to know the key difference between redaction and minimization. Know that minimization occurs before data collection, and then before or during data collection, and then redaction occurs after. So minimization will limit what is collected upfront, while redaction will remove the unnecessary data after the fact. So you can think of redaction as a way of cleaning up after minimization. And of course, data loss prevention and classification. Again, we can label our data based on the levels of sensitivity. We have public, internal, confidential, secret, and of course, top secret. And of course, we can apply regulatory frameworks such as GDPR, HIPAA, and CCPA. They establish the requirements for safe collection of the data, its use, transport, as well as storage. So if an AI system processes regulated data, then these kinds of controls must be in place. So key takeaways, the AI, of course, has risks to the CIA triad. Data breaches can occur. We have the issues of model bias. And of course, with data masking, you have both the static and dynamic masking. We can also apply anonymization, redaction, and minimization. Again, remember that redaction occurs after minimization. And then, of course, data classification, different levels. And of course, we also need to be regulatorily compliant when it comes to protecting and using our data. Thank you for watching. I will see you in the next class. Let's talk about prompt and log monitoring. So what is the purpose of prompt and log monitoring? Now, as system admins, it is required for us to capture, analyze, and also respond to how AI systems are performing in real time. So the whole idea behind prompt and log monitoring is to basically track how the AI systems are being used, what are they used for, and perhaps more importantly, who is actually using those AI systems. We also ensure compliance. We want to maintain alignment with regulatory requirements, and then also optimize performance. By tracking how the AI is responding to prompts, we might be able to identify bottlenecks and then remove them to improve the AI's performance. So what to monitor in the actual prompts? What exactly are we looking for? We want to look for the query and the response volume. So we count prompts submitted and then the responses retrieved to establish the usage baselines, and then also identify the peak usage times during the day. Is it between the hours of 1 p.m. and 4 p.m. or something like that? We want to track this to ensure that we can also plan hardware scaling to cater for these peak hours. And then, of course, measure the response accuracy and compliance. And so we want to ensure that we're also tracking the inaccurate response trend. So rising false or inaccurate responses may signal degraded or outdated training data. So the key log metrics to monitor: latency, the stop parameter. So did the user follow up or close the request? Helps evaluate session completion as well as user satisfaction. And then, of course, error messages, obviously, the token use, and then of course unauthorized access. These are the key log metrics to monitor. And we also want to monitor for unsafe behavior. AI systems must actively be monitored to detect harmful, policy violating, or manipulative interactions before they actually escalate. So we want to look for abusive or malicious content, the talk or use of sensitive or prohibited topics, and then contextual drift as well. We also want to evaluate the performance of the model itself. How is it performing? And we have the bilingual evaluation on the study. This evaluates language model performance, especially including the translation quality, by comparing the output of the model to one made by an actual human. And then we can also track the model drift. So this will continuously track and evaluate the model outputs over time. When outputs degrade from the baseline, we retrain the model to reestablish the accuracy standards. Now, we do have something known as the canary prompts. These can help us to maintain the system's performance, and these are pre-formatted prompts injected to verify that the model responses remain accurate, safe, and within policy limits. So think of it as a proactive way of ensuring that the system is up to date. And of course, log sanitization and integrity. We want to protect the integrity and the confidentiality of our log data. So we can sanitize for sensitive data like your PII. We can set the read-only permissions when necessary. And then, of course, when it comes to remote logging, we maintain off-site log copies that are not readily accessible to local users, ensuring a tamper-resistant audit trail. So key takeaways: prompt monitoring goals. We want to identify PQs, the model's response accuracy, and of course, we also want to ensure policy compliance. We log key metrics like your track latency, stop parameters, error codes, and so on. We want to detect for unsafe behaviors as well. We can use the BLEU that tracks the translation quality. And of course, canary prompts are a proactive way to ensure the system is performing at peak. And then of course, we want to track for model drift as well. So we manage that. And of course, log protection. Thank you for watching. I will see you in the next class. Let's now move on to performance and cost monitoring. Now, the purpose behind monitoring the performance of our AI systems is to ensure that it can meet the workload demand and that it is properly configured for optimized operation. So we track the prompts, the queries, as well as the workload response. Obviously, measuring the quality and accuracy of our responses are going to be very, very important. So we want to monitor the accuracy, the track request volume, as well as reducing supplemental queries. Ideally, when a user provides a prompt to the AI model, within the very first response that the AI model provides back to the user, that response should be satisfactory enough for the user so that they don't have to follow up like, oh, I need more information, or I didn't like the response you gave me, give me another one. We want to reduce supplemental queries as much as possible. Now, prompt compression, okay? This is very, very important because there are situations where, I'm pretty sure you've done it before, I've also done it before, where you provide a prompt that's very, very large to the AI model. Now, the idea behind the compression of these prompts is that we will try to reduce the complexity while still preserving the original meaning of that prompt. So this is especially useful in environments where tokens are being used. Obviously, the more complex the prompt is, the more tokens that AI system will very likely use. So we try to make those prompts as small as possible. We compress them while still maintaining the original intent so that the AI model knows exactly how to respond. So we preserve the meaning, we lower the token costs, and then we also speed up our inference as a result. So the whole idea here is we try to reduce the supplemental queries, we improve performance. So we monitor the queries, we analyze the gaps that might exist, we update the model, and we also reduce follow-ups as a result. So this continuous improvement life cycle is aimed at ensuring that the query volume will decrease over time as the model becomes more accurate and responsive to user needs. We also need to track the use of tokens and then monitor the cost. So AI systems cost money to operate. Monitoring will help the organization understand what drives these costs and how to control them effectively. So we can restrict the use of tokens, all right? We don't want users to have an unlimited access to tokens because these tokens do cost money. And then we can also monitor the number of requests and specific prompt usage to ensure the best configuration and billing model is selected for our organization. Also, workload and the hardware configuration. The idea here is that if we've noticed that there are certain AI systems that are being used heavily, one thing we could do is that we could upgrade the hardware of those models so we increase their computing power, the storage, and connectivity configuration. So we make those particular systems more hardware capable to meet the demands. And then vice versa, if we notice that there are systems that are of low use, we can reduce their hardware requirements to save money long term. But the whole idea here is that there needs to be a trade-off, okay? If we're going to spend all this money to upgrade these systems, there needs to be a justification, okay? We need to show that, yes, these systems are heavily in use. Therefore, spending money to upgrade them is a justification. So, data storage and retention policies as well, why storage matters. Storage of prompts, queries, and outputs used in subsequent prompts will speed up the processing, but also costs money. So careful policies are required to balance performance with cost. Now, there is the LRU eviction policy. You should know this for the exam. It's called the least recently used eviction policy. So this removes the oldest and outdated embeddings in system memory, the cache memory, or vector database when the system reaches its predefined limits. So we basically define our retention policies. We implement what we call the deduplication. We apply data eviction, and of course, we monitor the costs of storing all this data. And then, of course, comes rebuilding. Obviously, we want to rebuild and then retrain our AI models over time. Obviously, we don't want them to degrade. So we document the rebuild frequency. And obviously, when we're retraining our AI models, we need to retrain them on new data sets. We can't train them on the same old data sets we did so in the first place. What's the point of retraining if you're going to train on the exact same data over and over again, right? So we retrain on new data sets. This can help to reduce hallucinations and bias. So why retraining matters? Well, without regular training, AI models can drift from accuracy, producing outdated, biased, or hallucinated responses. So reschedule rebuilds are a critical part of responsible AI operations. So at the end of the day, it's all about cost-benefit analysis, right? We need to justify all this amount of money we spend on updating or increasing the hardware capabilities. If we know that these are AI systems that are being used heavily, we need to spend more money. So the system budget should be enforced at all times through careful automated monitoring, and we can do so by project. So we break down costs by individual projects to understand which initiatives will consume the most resources and deliver the most value. We can do so by customer as well. So we attribute costs to specific customers or user groups to enable accurate billing and identify high cost usage patterns, or by prompt input and output. So we compare prompt input and response costs against system computing costs for fine-grained operational insight. And we can also do so by automated monitoring. So fine-grained analysis ensures the organization maintains its established budget when operating an AI system at scale. So key takeaways: performance monitoring, very, very important. One of the ways to ensure system performance is through prompt compression. We save costs as a result. We can also monitor use of queries as well as the use of tokens. And then hardware right sizing. The configuration should match users. So we scale up for heavy use, scale down for low use to optimize cost and performance. And of course, we need to have storage and retention policies. And then, of course, we can rebuild and also apply cost analysis. Thank you for watching. I will see you in the next class. Let's move on to AI cost monitoring. So When it comes to using large language models like Claude and ChatGPT from a cybersecurity context, it's very, very simple and straightforward, right? We can provide ChatGPT with the logs from our firewall and then say, hey, check for any indicators of compromise, right? It's a very, very simple process. Unfortunately, though, this can be time consuming because we have to provide the information to ChatGPT, we can make errors and so on. But the real power of accessing models comes with the use of our APIs, our application programming interfaces. So without the APIs, the whole process can be very, very slow, error prone. But when we use an API, the log events will be sent directly to the model via the use of the API. And because we're using an API, we can actually enrich the response and even create the next steps for the model to take, such as generating alerts or even creating firewall rules. So how exactly does API integration work? We make use of the API key, which will allow access or programmatic access for our LLM. So it basically kind of acts like a way of authenticating and authorizing the AI model to make use of that particular tool with which it is trying to integrate with. So we get the API key for that tool, we connect, we plug in the tool, we select a model, and then we send the request to that tool via the API. So tools like your OpenWeb UI will connect to hosted models, for example, GPT models hosted by your OpenAI using this key. So when a user selects a model and submits a prompt, the tool will send the request to the LLM via the API and will then display the output or response all transparently as well as automatically. Now, because different models carry very different price tags, you must have noticed this before. All our major models, Claude, ChatGPT, they all have different models. Like, for example, at the time of me recording this video with Claude specifically, you have Opus and Sonnet. Sonnet is best for everyday tasks. Opus is far more advanced, but guess what? The more advanced the model is, the more it's going to cost to actually run that particular kind of model. So we can have premium models that will cost $5 per case, but in here you will get advanced reasoning, larger context windows, richer outputs, or you can go with like the economy model that are suitable for simpler everyday tasks. Now, we also need to restrict the API key access, okay? Because when setting up an API key, admins, we can restrict which models that key will be allowed to access. And the reason why we want to do this is because we don't want employees to start using the very expensive models unnecessarily, okay? If you're just trying to ask a very, very simple question, why not just use the standard economy model? Don't go and use the premium model to ask what is 10 plus 10, right? That doesn't make any sense. So this way we keep costs aligned with the task at hand. We enforce governance over the AI tool usage, and then reduce the risk, of course, of getting unexpected billing spikes. And we can monitor usage via the use of a dashboard. So API providers like OpenAI, they do offer dashboards that will show exactly how API keys are being used, as well as the costs of using those particular keys, which you can see right there. So at the end of the day, it's all about making cost-based decisions, okay? So dashboard insights will transform raw usage data into actionable decisions. Organizations can then use this visibility to optimize both cost and capability. So we can set spending limits, we can switch to a cheaper model if necessary, and then we can upgrade when we do have the budget to do so. Key takeaways: interactive and programmatic LLMs can be used via prompts directly or integrated programmatically via an API for powerful automation. And of course, API does enable automation. It allows the AI model to actually make decisions on its own, and then manage API keys carefully, model cost very widely. And then of course, day-to-day visibility, that's the use of dashboards. They provide granular cost visibility, enabling budget enforcement and smarter model selection. And then of course, it's an ongoing process. We don't just monitor AI on day one and then call it quits. Okay, it's going to be a continuous thing. Thank you for watching. I will see you in the next class. Let's now move on to the final lesson in this section. And here we are talking about quality and compliance auditing. Now, A big part of measuring an AI system's performance comes in terms of hallucinations and bias. So what exactly are hallucinations? They occur when the AI system will actually provide a plausible seeming response or output that's actually incorrect. And the funny thing about hallucinations is that many times the AI system appears to be very confident, all right? It will confidently tell you nonsense. So they're primarily caused by training on data sets with inaccurate patterns or data sets that have been biased or skewed toward a particular viewpoint. Now, this leads us to bias. Bias refers to the tendency of an AI system to produce prejudiced or unfair outcomes in its responses. So these are typically, again, caused by inaccurate or skewed training data, manifestation, plausible but factually incorrect outputs, and then, of course, the impact here is that you can have very unfair or prejudiced AI responses. So we need to measure for fairness. When the AI makes a decision, when it provides an output, is it actually fair? And fairness here measures how the system's output will treat different groups of individuals. And of course, this is a very important critical dimension of responsible AI deployment as well as AI ethics. So fairness, it is a regulatory requirement. And the thing though is that in attempts to ensure fairness, we may need to have access to restricted or controlled data, such as financial information, medical information, and so much more. So because we might need to have access to these very sensitive data, we need to introduce additional governance and, of course, privacy considerations need to be taken into account. So the objective here behind measuring fairness is to ensure equitable outcomes. We don't want the AI model to make discriminatory decisions against people of a certain kind of age range, sex, race, location, and so on. And of course, response accuracy. Ensuring responses are factually correct and specific to the request is critical. So like I said earlier, ideally, we want users to be able to provide their prompt, and then the very first response the AI model makes to that prompt, it is actually satisfactory to the user. So users should receive a correct, complete response on the first try. And each request made by the user to the AI model can be billed or ends up consuming a token. So inaccurate responses, because the AI keeps giving inaccurate responses, the user needs to keep on asking the same question over and over. This can drive up operational costs. So the goal here is 100%. Users must receive the most complete and correct response possible on every single interaction. And of course, we measure confidence monitoring and ground checking. Now, why this matters, organizations can implement response confidence level monitoring to gauge accuracy and then also isolate any potential issues of hallucinations, bias, or unfairness. And of course, we can do RAG tuning, the retrieval augmented generation tuning. This is a common tool for preventing hallucinations by anchoring the model outputs to verified external knowledge sources. So confidence monitoring, we track response confidence scores to flag low certainty outputs before they reach the end users. And then ground checks, we tie AI output back to trusted data sources to minimize the hallucinations. And of course, we can also implement RAG tuning. Now, when it comes to the evaluation metrics, there's two ones you need to be aware of, okay? The BLEU and then the ROG. So standardized evaluation metrics would allow engineers to objectively measure the quality of AI generated text against reference outputs. Now, we've talked about BLEU, the bilingual evaluation on the study. This is usually used for gauging how effective an AI model is at translation. Okay, so it's simple and widely used across NLP benchmarks. However, it doesn't take into account missing context or semantic meaning. Now, ROG, which is the recall-oriented understudy for gisting evaluations, this is better suited for summarization evaluations. So it looks at both the quality and quantity of the overlapping content It can also tolerate paraphrasing. In other words, it's far more flexible than your BLEU. It captures recall of key information from reference text. So the all steps involved in the evaluation metrics in here. We generate the output by the AI. We compare that output to the BLEU or Rogue, and then we score and evaluate. Hey, the AI model did well, it did poorly. And then, of course, we iterate and improve. And then the use of counterfactual testing and golden data sets. You need to know this for the exam. So counterfactual testing, we alter the input and basically observe whether we have system behavior changes. So this is actually a very, very powerful method for being able to identify bias and also ensure explainability in AI decision making. So counterfactual testing and golden data sets together form the backbone of trustworthy AI validation, ensuring that what the system says it does, it actually does. But what exactly would be a golden data set? These are basically data sets, as the name suggests, golden, that have the highest quality, okay? The integrity, the quality of the data in our golden data sets has been triple verified, triple validated. It is the absolute truth standard. So this would allow engineers to validate the system performance and behaviors are within organizational parameters. And of course, we ensure accountability and consistency with the use of counterfactual testing and golden data sets. Also, we can run routine log auditing. So routine auditing of all system logs will provide critical insight into how AI systems are being used throughout the organization. And in some cases, is legally compliance mandated. We do have certain kinds of frameworks or legal compliances that actually make this mandatory. So what the logs reveal? Well, they provide a view into the queries and prompts used as inputs, the permission change logging as well. So changes in system permissions should be logged and justified with approval chains. And then, of course, we can also run what we call automated auditing. So auditing can be assisted through the use of automated processes, reducing manual overhead while improving consistency and speed. Also, access log auditing and least privilege. We need to make sure that our access logs must be audited to ensure the system performance as intended. And then the least privilege principle, we need to apply this at all times. Separation of duties must be maintained to prevent log integrity issues. And then in large configurations with multiple data sets, models, and endpoints, access logs should be audited across the entire platform. Now, there is a particular scenario here that you need to be aware of. We call it the break glass workflow. So in this situation right here, we provide elevated permissions to certain kinds of users during an emergency, okay? So break glass workflows allow emergency use of elevated permissions by identified users in critical situations such as outages. However, we do need to control this as well. So before we grant these emergency elevated permissions, there needs to be a justification, okay? So authorization and justification of elevated permission use must be logged, okay? We need to log them. And then auto revocation. Just because we've given certain users elevated permissions doesn't mean that they get to keep those permissions forever, okay? Those permissions need to expire once the emergency has ended. And then, of course, a full audit trail. Every break glass event must be traceable, reviewable, and reportable for compliance purposes. So, key takeaways: hallucinations and bias, and of course, fairness. These are things we need to measure. Accuracy also equals productivity. So response accuracy directly impacts user productivity and will drive down operational cost. Know your BLEU and your standardized evaluation metrics. And then, of course, testing and validation, the use of golden data sets and counterfactual testing. And then, of course, we need to enforce least privilege, auto-revoke break glass access, and, of course, maintain separation of duties in auditing. Thank you for watching. I will see you in the next class. All right, so we've come to the end of this very special training for the CompTIA SecAI Plus exam. We have covered fully domains 1 and 3, but of course, like I said earlier, if you're interested in the actual main course itself, you're more than welcome to enroll. I will have again all the information done for you in the box below. So from the bottom of my heart, let me say thank you for finishing the tutorial. And if you're going to enroll in my main course, I hope to see you there. We'll continue this conversation there. If not, if this is the last time you're going to be seeing me or I'm going to be seeing you, it doesn't matter. I want to wish you all the very best in the CompTIA SecAI Plus exam, and I hope you pass that exam and you earn your CompTIA SecAI Plus certification. Thanks so much, and of course, I'll see you next time. Cheers.